Good afternoon, everyone. Again, my name is John Liu. I'm Deputy District Director for Caltrans District 6 Maintenance Operations here in Fresno. And want to welcome you, everyone, to day 2 of the ISOAP workshop. One thing we recognize is the day 1 had a lot of information. We had a lot of presentations that were just crammed full of information. A lot of speakers had to go really, really fast to get all the content in. Today should be a little bit more relaxed. And we definitely want to try to answer more questions. And we do welcome you to insert your questions in the Q&A box. We do intend to get written responses as well. And those will either be emailed to you or they will be hosted online and you'll be able to download that. So just to review what we are, the agenda for today. We're going to start going over about 15-20 minutes, a real quick review of what we learned yesterday. We'll maybe add a few things that we weren't able to talk about, but we also have time to also answer more questions, provide some answers. And then we have our keynote speaker, Brian Ray. He is with Sunrise Transportation Strategies, formerly of Kittleson Associates. He's going to give us a very compelling talk about, saving time, money, and lives through performance-based intersection evaluation and design. And he is one of our national experts, and we're just very fortunate that he's able to spend some time with us this afternoon. And then we're going to go into a little bit more detail in ISOAP for the analysis that's required for stage 2. And starting with calculating safety performance. And this is getting into the details of how do you calculate highway safety manual. And that's probably one of the more difficult things, working through the new ISO process. So we have Gina and Bernice from Headquarters Design, as well as Jerry Chamfa. And afterwards, we have Lillian Wu from Headquarters Traffic Operations. She'll talk about calculating the performance, the DPHD, and what are some of the tricks needed to calculate the performance mobility outcomes. We're going to have a 10-minute break, and then right after the break, from District 6 Materials, we have Mohammed, and he's going to talk about intersection pavement design. A lot of considerations in deciding whether to go concrete or HMA, asphalt. And he's going to dive a little bit deeper on why we would maybe consider one or the other and some of the cost implications. I'm going to go through a case study from District 9 over in Bishop. This has both stage 1 and 2 of ISOAP. So this is a real life example. And then I'm going to talk about locally sponsored projects and local development review. How does ISOAP work with these locally sponsored projects, or these projects that are working through local agencies? And also, what are the roles and responsibilities of the various Caltrans staff, as well as maybe consulting engineers who are working on an ISOAP? We're going to talk about public outreach. A lot of times we're suggesting things that may be controversial. So how do we deal with the public? What are some tips? So I'll try to share some from experience. Jerry's going to have an exercise. We've got more time for questions and answers, and we will wrap up by 4:30. So this time I'm going to pass it over to Jerry Chamfa. Again, he's our retired annuitant from the Headquarters Safety Programs, and he's going to do a little bit of a review. Jerry.
Okay, thank you. I want to say good afternoon to everyone who's joined us. Welcome again. And as John said, I work for the Office of Safe Systems Approach Integration. So I do want to kind of review in order to either emphasize or cover things that were missed or just glossed over yesterday. And of course, one of the foundations of what we're doing through ISOAP is we're looking at accelerating, increasing the implementation of safe system intersections as solutions, as improvement strategies. So real quickly, this is one snapshot, the first slide, just to show you again what the publications, the resources are that contain these strategies, information about them, guidance, and basic application guidance, I should say, and right down to including performance metric information, the crash reduction factors, and how these strategies work. And so on the right-hand side, again, I do want to emphasize one last time that what makes a strategy, an intersection type or strategy, a safe system strategy is its ability, its alignment with these safe system objectives in the roadway design hierarchy. And tier one and two, of course, are the most important, removing severe conflicts. That's the most important objective that we can pursue to improve safety at intersections and the operational performance and capacity. And then, of course, reducing vehicle speed. Intersections that can do that are also without impacting mobility. Those are very desirable intersections as well. Let's go to the next slide. And also, what I did not cover yesterday, I just wanted to show this. This is in the roadway design hierarchy document as well. And it's one of the things on how to use the hierarchy. And it covers, just a snapshot of how this would work to apply it to a project that's trying to create a complete street. So I'm not going to go through the details here, but this is the kind of information guidance, general guidance that's available in the document. And I think the link was on the slides yesterday. So, John, let's go on to the next slide. And again, what we talked about just now, one of the tiers is removing severe conflicts. So this was a slide from yesterday. And this, again, is just an example of the conflict analysis diagram for the restricted crossing U-turn configuration. And what's important here is that this is one example of, I think the standard intersection has up to 54 conflicts. That would be just a regular stop controlled or signal controlled, up to 54 potential conflicts. This is showing you that the arc cut has a total of 24 conflicts. And the connection here is actually that the reduction factor for using implementing an arc cut is about 50 or 60%. So what you see is there is some actual parallel. The conflicts here are 24 compared to 54, about a 60% reduction in conflicts. And lo and behold, the reduction factor for implementing an arc cut is about 50 to 60%. So that shows the importance of reducing these severe conflicts. Next slide. And this is a summary of the intersection conflict analysis findings. Again, this is in an FHWA public research publication. Our cuts are on here and got that information about, I believe, about the conflicts for that. Yeah, that's covered here with an, as you can see, collision reduction factor at the end there, 54 to 63%. And so you have this for a quick comparison with other intersection alternatives and control strategies. So that's a slide that's also from day one, and now you have that here as well. And then, we did talk a lot yesterday about the design of roundabouts. We talked about the advantages of roundabouts. And one of the things we really didn't get a chance to do yesterday was talk about some of the issues that we want to clearly avoid at roundabouts. And this can be a design-related issue. I'm not saying in this photo where a truck actually blocked an intersection for several hours. I'm not saying this was a result of a bad design decision or poor design. This could have been driver error. In any event, the point is this is the last thing we want to see happen. Is about the worst thing that can happen at a roundabout. And this is something why, as Gina Lopez yesterday emphasized, the need for checks on the performance objectives of roundabouts. The performance checks are critical to make sure that our design is not going to create this problem. And John, go forward again. And so going back to roundabouts, this is a review of yesterday. Just wanted to show a side-by-side comparison of what we talked about when we were talking about affordable roundabouts, smaller roundabouts, in this case, a mini roundabout on the right side of the slide at an interchange ramp in the state of Maryland. Again, compared to what the standard conventional practice has been. The mini in this case functioning adequately is about half the size. Question is the cost about half, and is the performance as good as you would get with the conventional? These are things that we're learning more about all the time. But obviously here there's a broad range of applications and design designs for implementing roundabouts now, and the more affordable ones are certainly what we want to make sure we consider when we're doing an ISO evaluation. And last but not least, yesterday, again, talking about affordable designs, Phil Rust gave a presentation on two things, really: the city of San Diego's Vision Zero intersection safety program and how it is featuring not just roundabouts, but affordable modular roundabouts. And again, this is the last from his slide, I think, again, showing how these 4-foot prefabricated durable plastic curbs, again, with a very strong anchor system to the pavement. As Phil was saying, this has been designed, tested, piloted, evaluated, redesigned, and strengthened over a 10-year period. So in this case, we're putting in what would be a quick build, low cost, but permanent installation. I just wanted to emphasize that these can be permanent installations, not just temporary or interim, even though they are modular. Okay. And I'm hoping that with those slides, maybe that will help generate a few more new questions. So that's all I have.
Okay, and there is one slide that I want to cover for review, and that is the city of Modesto. So we talked about the intersection of Claritina and Coffee. And on the left side, this is a picture back from around 2012. They had this quick build roundabout. It's been in place over 10 years. And the intersection was designed to have a very large signalized intersection, and this was the interim configuration. And then a couple of years ago is when they decided to upgrade it, not to a full-blown standard roundabout, but it's what they call a quicker build. So it has a lot more permanent types of elements, meaning it actually has a proper central island. It has splitter islands, and you can notice that they're not very long, but they are concrete islands that are doweled into the pavement. So it's very likely that as the corners are developed, this will eventually become a traditional permanent roundabout. But this is something that is very functional, and they like to say it's imperfect, but it works. It works very, very well. And this is a location where the public actually wanted to keep the roundabout rather than going to a traffic signal. So we know that a lot of times roundabouts are very, very controversial, but once you get one well-designed roundabout in, a lot of times you're able to kind of turn the tide on the controversy. But it is really important to have that first roundabout be designed really, really well. That way people will really see and appreciate how well that they really can operate. Okay, so we don't have any other questions. So before we get to Brian, a couple things I just want to mention is ISOAP. The process is designed to be very, very flexible. And that's one thing that when we work with HWA and their consultant VHB and looked at all the ICE policies and procedures across the country, and approximately a third of the states have some sort of form of ICE. One of the things they really liked about ours was it provides a lot of flexibility. There's a lot of engineering judgment. There's not a lot of prescriptive process. You know, some states have these very, very thick manuals, and they're almost like black boxes where you put all the inputs and it's going to spit out your answer. Hey, these are the types of intersection control and forms that you should look at. And I think yesterday Bastian made some very, very good points that sometimes when you depend on these processes, it may screen out something, configuration that actually should not be screened out, because it really should all be iterative. You shouldn't be looking at any one aspect, in a silo, in a vacuum, because it will affect, the performance of one aspect could potentially affect a different type of performance of how our intersection operates. And ICE or ISOP is not just about roundabouts, but just to kind of reiterate the point, it really meets a lot of what the safe system approach embodies. It lowers speeds at conflict points, generally very pedestrian friendly. For bicyclists in District 6, we always like to provide a shared use path to give options for the bicyclists who may not be confident riding with traffic, particularly with multi-lane roundabouts. So we are currently doing some research with Fresno State, and this research should be published within the next couple months. But one thing the research is going to show that there really needs to be a lot more education, particularly with the regard with pedestrians as to how roundabouts operate. So I think that's an area that we do have a lot of opportunity as we are potentially going to be building a lot more roundabouts, not just on a state highway system, but we would hope on the local system as well. Okay, so that being said, yeah, Jerry, you want to add something?
Yeah, I have a question, and I'm going to ask a question I've heard a lot, and I want to ask this because you just said something that reminded me. And I think during the last few months in various workshops, we've been asked about warrants and warrants during the ISO process. And people in particular have wondered, where do you find the warrants for roundabouts? We all know that always stop and signals require, there's a warrant, engineering warrant study requirement. And of course, there is no warrant for the consideration and use of a roundabout. And that has been the case since day one with roundabout practice in the US. And what you were saying was reminded me that probably one of the reasons why there are no warrants is because there are so many positives, and there really can't be, or there are not negatives, except for when you design one, build one that's not well designed. As you could see, you could have problems with design vehicles. But that's something that education, it's good news, but that's part of the education process moving forward, at least for the engineering community. So thank you.
Yeah, and one reason you have warrants is that helps you decide where you want to do a particular type of feature, but also where you do not want to consider a particular type of feature. And one issue that you may come up is you may have more locations that you want to build roundabouts that you have resources available. So you'll have to come up with some method to prioritize the location, whether it's dealing with the number of crashes, it could be a benefit cost ratio. There's different ways of looking at, where do you want to do the next improvement. One of the things we talked about was trying to make roundabouts more affordable. As Jerry talked about yesterday, is a typical roundabout on a state highway system now is $8 million or more. And if we can get the roundabouts to be smaller, we still want to have good performance and have the good safety outcomes, still have the mobility that we need. But we would like to implement roundabouts, systemically, so that way the benefits could really be spread out much wider. And our goal really is to save lives. So the more roundabouts or other types of safety improvements, it could be just more it could be more raised medians and just requiring people to make right in, right outs, U-turns. It's really important to look at a network and make those decisions. Where should those the nodes be where people are able to make full movements, and what's the appropriate type of treatment at those locations? It could be having roundabouts every quarter mile, every half mile, everything in between is right in, right out. So it's really good at a planning level to work with our local partners and just lay out on our transportation concept report or multimodal corridor report, as we have in Caltrans, work with the local agencies with their circulation elements and really plan out. Ultimately, this is how the state highway system should look at in the community. So it really serves the community, serves all their needs, not just for the motorists, but also the pedestrians and bicyclists and transit users.
John,
Yeah.
One more note just about the agenda moving forward. I forgot to mention that we hope to show a video. We're not going to cover I don't think affordable roundabouts or modular in particular, but we do have a video to show during the break. So as you're coming back to the break, it's a very short video on the installation of a modular roundabout, which again, as Phil Rust did a great job yesterday of explaining how much time and funding can be saved. And of course, getting roundabout improvements out there is part of their goal. The more quickly they do it, the more you can prevent severe crashes. So I think the program that San Diego has created, established, and pursuing is extremely important as we're looking at our safe system goal of small, low-cost improvements at as many high-risk intersections as possible. And my exercises or exercise will hopefully bring out some of the flexibility, the streamlining that is available in the ISO process. So I want to make sure that folks, if you're interested in that, that you stick around till the end.
Yeah,
Thanks.
great. Okay, next on deck, we have Brian Ray, and I'll let him set up, but as he does that, I'll go ahead and do a little introduction. Brian Ray is just a great friend of Caltrans. He has over 35 years of practical experience. He's supported Caltrans since 1999, when we were just starting to explore, roundabouts on the state highway system. He's been involved with numerous national research publications, applying performance-based planning and design, including ramp and interchange spacing. He's one of the diverging diamond experts, and he's worked on the new roundabout guide, NCHRP 1043. He supported Caltrans since our original ICE policy of 2013, and he also has his fingerprints all over ISOAP. He helped us make ISOAP that much better, so I really appreciate what Brian has really contributed to Caltrans. So I'll just go ahead and pass it on to Brian. He now has his own firm. He's the sole proprietor of Sunrise Transportation Strategies. So Brian, it's all yours.
Great, thank you. When I was coordinating with John and realizing a little bit of a bio and going back in time of how far back, it's a little bit alarming, but it's also really exciting to see the progress. When we all first met back in 1999, at that time, Caltrans was actually exploring the first time, what's it going to be like to be potentially putting roundabouts on the state system. So that's pretty darn amazing. That was 25 years ago, and here we are today. So we've really come a long, long way. When Jerry and John reached out to me about the topic, saving time, money, and lives through performance-based design, they didn't really give me a lot of an outline of where to go from. So this is going to be probably new to them too. And one of the things I like about it is the trust with Caltrans of being able to share perspectives, and what I hope is create a little bit of a conversation. So what I want to do here is just talk a little bit about an overview. Let's get ourselves set up, highlight really where and how your decisions can save lives. And that's one of the most amazing things for us as engineers and planners. And I say planners too, because design doesn't begin at design. And if we look through the NCHRP document that Gina talked about yesterday, report 785, performance effects of geometric design, the choices that we make in project planning are absolutely so critical. So your PID process, all of those activities, the choices that you make there really help you save lives. And so it's beyond engineering. I want to share a little bit about ISO, talk a little bit about ISO, some of the elements of it. What I really want to have you do is recognize is talking about having the courage to say yes in what we do. And we'll go through that. And what I hope is that it lists at least some questions that we can have a conversation. So from an overview point of view, one of the things I love about working with Caltrans is that you try to push the boundaries. And whether that goes back to the late 1990s of context-sensitive solutions and trying to be thoughtful about the community, you can look back through at a lot of the director's policies about being progressive and trying to make positive changes. And so, as you've heard today, is it's very, very clear that Caltrans supports performance-based approaches to reducing severe and fatal crashes. And you have the opportunity, whether you're Caltrans or the consulting, you have the opportunity in your planning design decisions to save lives and money while you do it. That's a powerful, powerful opportunity for us. And it's exciting because those lives are your own family, they're your friends, they're your neighbors, they're your community. And what's really interesting is Caltrans has been applying performance-based planning and design activities, even if your HDM hasn't caught up yet. Your HDM is a giant manual. It takes a lot of time and effort to go back through and update everything that's happening there. And there just isn't enough staff time to do that. But your staff is extremely progressive in looking at and introducing the policy directives, identifying these guidelines, the interest of using new national guidelines, the reference to the Federal Highway Administration. So just because it's not in the HDM doesn't mean that it's not a good thing. And as a matter of fact, there's a lot of really good things there. And as Gina showed yesterday, especially with roundabouts, there's tremendous flexibility in your HDM, and the ability to apply new guidance helps complement and support the decisions. So why do we even want to do these performance-based approaches? Well, it's because of the effectiveness of the results and the value-focused solutions that come from the processes. That's the key word, value-focused. The whole intent of performance-based practical design is I'd rather have 10 miles of good road than 1 mile of great road. And that money that we save at one location through high value can be distributed and used in other locations. So we have a lot of power in applying performance-based approaches. So what are performance-based evaluations? Well, they focus on the outcomes versus prescriptive dimensions or solutions. And I loved Gina's slides yesterday that she had talking about nominal safety versus substantive safety. That an 11-foot lane is not necessarily a horrifically dangerous thing. A 12-foot lane isn't necessarily perfect. An 11.9-foot lane isn't going to be tremendously different than a 12-foot lane. So we have the ability to think more about the overall project performance. But NCHRP report 785, and anytime I talk about NCHRP, it's the National Cooperative Highway Research Program. NCHRP, any document that I reference is free. You can download it for free. But 785 said, when I'm looking at any project, I have two fundamental questions. What are we trying to achieve and whom are we trying to serve? And we set up those very basic questions, because if you go back to asking those things, what are we trying to what are we trying to achieve? If it's a safety-based project, it shouldn't lead to high capacity or higher speeds. If it's a community building project, it shouldn't lead to widening or other elements that take that out. And whom are we trying to serve? And sometimes we're trying to serve big trucks. Sometimes we're trying to serve high volumes through an interchange. But many, many times we're trying to serve a wide array of people. And if we can make sure that we're understanding that, it can help us with our decision making. So where this starts is really identifying what our intended project outcomes are and what is the target performance that we're trying to get. What were we trying to do? Is it a low speed environment? Is it a gateway coming into a community? Is it a higher capacity location? But when we understand what we're trying to do, it gives us a great start on our roadway geometrics, the intersection form, the roadway approach. And so it gives us a chance to start aiming to what we were hoping to get. And when we're going towards that target performance, we optimize and look at that to be able to attain those performance targets. And so if we actually get our geometrics to meet the performance targets, we can actually get our intended project outcomes. And so one of the things that you'll see in your ISOAP early on in stage one is a conversation of what are the intended outcomes. And that's different than a project's purpose and need. It's compatible with the project purpose and need, but it allows us to focus in on the geometrics, the form, what is it that we're going to leave there, and how can that guide some of our project decisions? So this initial model, Gina showed a little bit about that yesterday, but this initial model itself starts from reflecting what is my project context, what are my outcomes? So again, that's right what you'll find in stage one of ISOAP. But it says then, let's let that become the basis for starting our geometric influences. We'll identify potential solutions, we'll test their performance, and we'll iterate, we'll refine to optimize. And this model itself was actually used by the Federal Highway Administration in their performance-based practical design manual. Gina talked a little bit about performance-based and practical design yesterday. But performance models have been around for a while. They were around originally in the first Federal Highway Administration roundabout guide from the year 2000. They got integrated and expanded into NCHRP report 672. And we really expanded them out in NCHRP report 1043. And I encourage you to look at chapter 9 and chapter 3, and it'll outline a design process. And when I'm giving a conversation about that guide, what I say is skip the word roundabout, and you could use that framework for any intersection that you're looking at. And Caltrans' initial policy, 2013, was performance-based. And what's really nice is ISOAP expands upon those tools, much more reflective of where industry has continued to evolve, especially moving towards that aspect of fatal and severe crashes. I've always been a champion of Caltrans' ICE policy and ICE activities. I've always found that the flexibility in the ICE was really a benefit compared to a very restrictive, prescriptive approach. I'm hoping that when we look at ISOAP, It still contains the value of the flexibility and the engineering judgment without being too prescriptive. And I think ISOAP is going to be a really nice positive change in addition to go on from where the ICE policy was. So I want to just highlight that performance-based evaluations and performance checks aren't just part of Roundabouts. When we did NCHRP report 959, the Diverging Diamond Guide, it actually is based off of looking at real case studies and examples that were elements that we might want to do differently, legacy elements that we don't want to do anymore. So it identified some general performance categories, verifying that design users are integrated into the process, not accommodated later on, but integrated into the design. And even chapter 6 highlights that beginning to do your DDI design. It says start from the inside and work out. That's from the pedestrian area, if that's where it's going to be, and work outwards from there, from the center of the roadway and out in terms of your crossovers. But it goes back to the fundamentals of intersection design and roadway design, stopping sight distance, intersection sight distance, view angle considerations. And so if you're thinking about the roundabout performance, you've done those speed checks, you've done intersection sight distance, you've looked at view angles. And so what we see here in this example from chapter 6 is a legacy element. If you look at the northbound right turning of that graphic, it's a very, very flat angle. That driver has a terrible view angle for a design speed of 20 miles per hour. And if we look at a more contemporary design of the DDI, a contemporary way to serve that northbound right turn for that same stopping sight distance, that same intersection sight distance that we have a much better view angle. So performance checks aren't just for roundabouts. They can really apply to all of your intersections. But there are unique elements about DDIs and some of the performance checks. So some of those really come down to a speed profile, looking at how drivers are coming into that transition from the segment to the first curve, the second curve, the crossover, working their way through. There's information about an approach vista of what do the drivers see when they're coming through. And so some of the things you'll see here over to the right, is it fully blocked? Is it partially blocked? Or is it not blocked at all? And these become part of the ways that we can test and check DDIs and look for ways to optimize them. Path alignment and view through the vista are other two elements. And if any of these terms are new to you, I encourage you to look at chapter 6 of the DDI guide, because many of these follow the same basic principles from the roundabout guide, the work that you're experiencing before. ISOAP, it's a pleasure to have been able to offer some input about ISOAP. One of the things I tried with John was get rid of the word process, just stop it at the A. Let's just have it an assessment, but I couldn't make that influence. So now, just like the word automatic teller machine, ATM machine, you have the ISOAP process. So now you have ISOAP process. So we'll get there. But as we had talked about yesterday, if you listen to Bastian, it's really an intersection control methodology. And this methodology itself has been evolving nationally since the 2010s. And again, Caltrans was a really early adapter in doing some outstanding work with the ISOAP. But other states have expanded the ICE tools and evaluations. SPICE is the safety performance of intersection control evaluation. It was a planning level tool prepared by the Federal Highway Administration. CAPX is a very, very simple approach to using planning tools to test capacity and operations. They're all meant to be aid and guide what you're doing. And one of the things I think is most important that John Lew had indicated is the tremendous flexibility that you can use these tools, but you're not obligated to use these tools. You can use rules with them. You can use other methods. And of course, if you have the data, you can go in and do more evaluation in a little bit more detail. But the intent is to be flexible in making your choices. And this is one of the things I think is exciting about where ISOAP can go. And again, there is that national guidance. And so there's the national guidance that Bastian covered yesterday that might provide some insights and some elements that support your ISOAP decision-making. So even though it's a different document, and even though you have your own guidelines, this is a way for you to take other experiences and incorporate that to do your work. But what we also want you to do is, just like Jerry was mentioning, some of the safe system approach, the SSI safe system for intersections. There's a lot of other national guidance out there, and all of these can complement what you're doing with the ISOAP. So The ISOAP guide, the process guide, is a great framework for you. It helps you get along, but I don't want you to be restricted to it. Don't be limited by it. And I want you to be comfortable using other tools, other areas. And the key is to document what you're doing, have conversations with your project team, and use this other information. So use ISOAP for good and not evil, okay? So in summary, performance-based analysis and design is really excellent because it allows us to tailor solutions to meet project needs. And I know you're used to the HDM, the Highway Design Manual, but if you were to look at the 2017 ASHTO policy, what it identifies is the ability to categorize your projects as new construction, reconstruction, where you're making a fundamental change to upgrade the facility, or reconstruction, where you're essentially reconstructing on the roadway and leaving in its present form. If we start with some of those as the basic category of project, it means that we can establish design criteria tailored to meet that project need. But it gives us flexibility in design. And by identifying what we're trying to achieve, it allows us to justify. So if we know we're working in a roundabout, we know we're working in approach geometry, then having 35 or 40 mile per hour speeds on a state highway can be okay. We don't need to justify 55 or 65 mile an hour curves if we're at that roundabout. It allows us to use the performance in that roundabout influence area to be able to make design decisions. What's fantastic about the intended outcomes, and you'll see that's part of what's in stage 1 of ICE, is it allows us to optimize the value of the project solutions. But what we can also do is by really documenting what we're trying to achieve in a project, it allows us to reduce our liability. And that's an important part of our decisions. Design flexibility without any reasoning isn't very good. But having a basis from which we start our design, using design flexibility, documenting it for the conditions that we identified and agreed upon at the beginning is what helps manage our risk. But I have to tell you, moving away from dimension-driven design is scary for some folks. They're used to looking up a chart. What do I do? How do I do this? Where does it come from? And so some of this is just going to take for you to be developing your skill set. And I'm going to go into that, but developing your engineering judgment. But the most important part here is you can do this. This is the way our industry is going, and you have the opportunity to make this happen. So let's just talk a little bit about the decisions that you make. Your decisions save lives. That's a fantastic responsibility. It's an honor. It's what I love about being an engineer. And Gina's really explored and been expanding and integrating the Highway Safety Manual into the Caltrans practice. But what's fantastic about the HSM is it really helped us identify crashes or collisions, not accidents. And it also led us to think about safety performance, that we don't want to improve safety. I don't know what improved safety is, but I can talk about reducing crash severity and fatalities. So I can now really quantify safety performance and speak about it in a way that we can measure it. But I wonder how many of you out there at Caltrans know that you have this glorious document from 2010, Complete Intersections, the guide to reconstructing interchanges and for bicycle and peds. Yep, it's 2010. Some of the data is a little bit old, but the principles and the fundamental elements in that document are outstanding and they still stand. And so Caltrans policies and directives are really moving towards saving lives. So as you're looking at your own documentation, as you're looking at your policy directives and initiating those, you have that opportunity to do it. So the choices that you're making, and as we heard from Jerry and Phil Rust about where the crashes occur, you have the tremendous opportunity to affect in your intersection design to create a positive effect for pedestrians and bicyclists. Your decisions can save lives. Fantastic. The intersection evaluation is probably your biggest opportunity to do that. When we think about run off the road programs and we look at your highway safety improvement program, yes, there's a number of areas that we want to address users' needs and special. But as we know, our intersections themselves are really those critical pieces. But if we're really going to go towards vision zero, if I'm in a car, a truck, another vehicle surrounded by steel, I'm relatively protected in some of those crashes. It's those vulnerable users at intersections that are most critical. And so if we're really going to go to vision zero, we really need to be thinking about the aspect of pedestrians and bicyclists. So that's really where we're going to have the biggest mark of saving or helping those vulnerable users. And you have this fantastic pedestrian safety countermeasures toolbox. It's a fantastic document, identifies an array of treatments and elements to consider. And all of these are consistent with your intent for ICE. Jerry's pulled up this document a number of times. It's a safe system approach of setting up our priorities and our planning and design decisions. And even if you're just starting to look at the tiers, and we'll go into those, and Jerry mentioned those, we don't have to quantify everything. The Highway Safety Manual allows us through predictive tools to predict crash numbers. But even if we're looking for comparative evaluations of speed, crossing distance, the vulnerability of pedestrians, even without having quantified data about a predictive crash, if I'm comparing Alt 1, Alt 2, Alt 3, I can use these highway design hierarchy and safe system approaches to compare and assess my alternatives. That's hugely powerful. And it's a great way to look at things while we're not able to necessarily use the Highway Safety Manual. But the really important part here is to really understand intersection planning and design, the fundamentals of that. A roundabout is just an intersection. That's all it is. It's an intersection. It's a specific type. And we have to understand the intersection planning and design principles. We're applying those to roundabouts. So what I'm going to do is encourage you is to really learn intersection design fundamentals, interchange design fundamentals, the quality of service fundamentals that help support the comfort and safety and security of our vulnerable users. You can do this. So let's talk a little bit about ISOAP. Some of you may or may not have known a fellow by the name of Paul McClintock in District 5. I know Jerry did, but one of the things that Paul said about your ICE policy was you should be able to do a step 1 ICE on the back of a napkin. And he meant it. He was serious. You should be able to go out and look at that intersection, document it, and use good judgment and experience at that location. And I think that that's a really important consideration or attempt. But ISOAP is 2 stages for a reason. 2 stages for a reason. It's meant for fast and efficient screening of inferior concepts. Now, that doesn't mean you want to go so fast that you're ignoring, but it does mean that you want to be quick and easy. And I'll talk a little bit more about that. But what you're looking for is you're trying to advance the promising solutions for more detailed evaluations. And keep in mind that like ICE, ISOAP itself doesn't select the alternative. You have a project initiation document phase, you have PA and ED. There's a whole series of activities in your project development process that help support. ICE and ISOAP are elements that help support, inform, and guide the project decision-making. The principles that Paul had indicated still stand. You should be able to work flexibly, efficiently, and don't draw things out that you don't need to have there. And this is really the part I would say is focus on the A, the analysis portion of ISOAP, and don't let the P portion of ISOAP, the process, take control. Understand what ISOAP was meant to do. Understand the flexibility. Understand the intent of stage 1, of stage 2. We don't want you so caught into process. Did I check every box? Did I make everything happen? We want to be really careful about that. And the key to ISOAP is really following what Jackie Leash, the Leash methodology, is the systems planning and functional design process. But what it's saying is I want to do just enough work to answer the key questions at hand. And so I want to screen and advance those alternatives. Now you want to be careful. I've worked in 2 districts where in the ICE activities, somebody felt ICE step 1, they felt, oh, we don't need to do the performance checks. We can do those performance checks in ICE step 2. And in getting engaged with those projects, those performance checks were really, really critical. And when we got into ICE stage 2, step 2, there were some really challenging locations in terms of the project impacts, the project footprint. So do enough work to screen. Don't do too much work, but be careful. You always want to do those performance checks. And if you're not sure what you're doing, ask. You have an excellent, excellent array of folks at headquarters, subject matter experts in your district at headquarters. Tap into those folks. So work smartly. And this is really one of the things if I was going to go back into ISOAP is try to make a change, is recognize that there's intersection form and then there's control strategy. So we heard a little bit about this, but I want to make this really clear. So the form first allows whole categories to be screened out. So if you're looking at an interchange form in a tight, constrained environment, built up around it, or environmentally sensitive, I know I'm not going to be able to do partial cloverleafs, L9s. If I know I'm not going to be able to do that, I can look at diamond forms, I can look at partial cloverleaf forms, and I might find that I can eliminate an entire array of interchange forms because of the constraint. Then I can look at the control strategy. Should that interchange form, should the ramp terminal intersections be stop, yield, obviously roundabout, or signal control? So form first, but if I can eliminate a whole family of interchange alternatives because the form isn't appropriate at that location, I can save time and money. I can focus in on the other things that are important. So remember that a restricted crossing U-turn, a median U-turn, a displaced left turn are intersection forms. They're forms. The control strategy, at least for a median U-turn and R-cut, those can be stop and those can be signalized, or we can do a bow tie configuration and have them be yield. So form first, control strategy second, and that's going to really help you make things more efficient. And even a diverging diamond, the fantastic diverging diamond, makes every day just a little brighter. It can be signalized, so it's a form, it's a diamond form, but it can also be yield control. And there's a couple of diverge-abouts in the United States. There are more of them being reviewed and looked at. And oh, I don't know what that is, excuse me. So anyway, that's the key. Form first, traffic control second. So when you're looking through your ISOAP, it's going to be really easy to just pull up the list. And what I'm going to tell you is that you want to be thoughtful about how you apply the solutions when you're working at the list. So I was just at the, last week, I was just in Atlanta at the Transportation Research Board Roundabout Compendium and International Symposium. And there was this huge push, it seemed to me, for everybody to want to come up with a fancy new name of what their roundabout was going to be. I heard something called a super spiral and a turbo-esque and a turbo diesel, you know, just this ridiculous thing. Don't do that. There's always going to be a new interchange form, a new intersection form. Somebody's always wanted to coin a fancy name. But that doesn't always mean that just because it's out there, whether the form is appropriate. So this is a list of what's called control strategies. But what I will tell you is these are actually intersection forms, not control strategies. So we've got to watch that out. But a continuous T intersection is for a three-legged intersection. So if your intersection is a four-legged intersection, you don't have to look at a continuous T. You don't have to go down that list. An echelon and a center turn overpass are grade separations. So if you've looked at your project, intended project outcomes, your budget, your situation, and the environment around it, neither of these are going to be appropriate for you if you don't, if an at-grade solution is what you're looking for at that location. And I'll tell you that the echelon has been around in name for probably 20 years. I don't think there's actually an echelon on the ground that I can find. I did some search. It's been investigated. It's got a super cool name, but I don't know if you can find one that's actually in place. So anyway, be very careful about that. If your location doesn't allow, it isn't appropriate for grade separations, then you don't have to look at these. Don't spend any time in this stage one. And remember, a pedestrian hybrid beacon is really for pedestrian quality of service. It's an outstanding form. It's an outstanding control. We want to think about all types of high visibility intersection forms, but be thoughtful about where and how it goes. And remember, a diverging diamond is just one variation of diamond forms. It's a great form because it has that displaced or relocated left turn that reduce crash severity. But there are other diamond forms too that have those same qualities of a DDI of displacing a left turn and reducing that crash risk. So the important part for you is you have a list. Consider this as a starting point. Consider this as something to get your mind going. But what I want you to know is that anytime this list is put together, it's never going to be comprehensive. There'll always be something else. So be careful of that. Work the solution, don't work the list. So this is a quote from the Roundabout Guide. A turbo roundabout is a multi-lane roundabout that uses spiral road geometry and physical channelization to maintain lane discipline in the circulatory roadway. I wrote that. That's chapter 10. The reason we wrote this is that the term turbo is one of these exciting new names. Woo, it's a turbo, it's a super turbo, it's an inverted turbo, it's a hyper turbo. The whole point is we get caught into the names and forget what we're really trying to do. It's a multi-lane design. We had issues where lane discipline isn't there, and there's physical features to do that. So this is your SR 156/25 intersections. Not all turbo forms have to be of this Dutch variety. This Dutch variety, this Dutch style shape is really excellent in the constrained environment. It was really appropriate to address that merging and diverging on the skewed intersection approaches. Those physical forms and elements were a great solution at this location. Fantastic, rock on, good. But we can also, though, introduce turbo characteristics or turbo elements. And this is an example in Sarasota, Florida, where it's a multi-lane design. It has raised features with the intent of supporting lane discipline. So the reason I say that is I just don't want you to get caught up into something that's shiny and exciting, and recognize we can borrow from and we can use the same elements and move away from the shiny names and think about the performance that you're trying to achieve. What's the performance I want? I don't want people changing lanes in my roundabout. That's where it comes from. And this is just an example of one of the approaches on this roundabout. It has path alignment that aims you into the circulatory roadway. It has physical features that help keep drivers in their lane. It uses raised pavement markings and enhanced striping to support the lane discipline internally. And what interesting enough is the Georgia DOT is beginning to introduce raised features on their roadway approaches for their multi-lane design. Not necessarily throughout the roundabout, but at least on the roadway approaches. So I want to share that with you because I don't want you to get caught in the name of turbo and suddenly think you have to have the mystique of hiring an expert. No, it's a turbo as a way to keep people in their lanes. The features are the same. So hope you're catching that. So learn the forms and then use the correct names. So these are names over the years of these intersection forms that were used to market and sell the form. Some of these were actually sold. So a CFI, boy, I wish I had thought of the word CFI. A continuous flow intersection takes a single intersection and breaks it into 5 other signalized intersections in total and still has the nerve to call it a continuous flow. Man, you gotta love that. Super street. Ooh, gosh, that makes me feel good. I got a super street. I have an urban interchange. Wow, I can only use my urban interchange in urban areas. Or I have a Michigan left. I guess it won't work in California. It won't work in Florida. Did you know that a hawk signal? I hear that. I was at the conference last week and somebody was asking me about a hawk signal. It was actually originally called a hawk beacon. And hawk stands for high intensity activated crossing. It's one of those crazy things that somebody saw that the British, who have pelican crossings, toucan crossings, and in Tucson, Arizona, somebody wanted to create this beacon and came up with this high intensity activated crosswalk and then put the name Hawk to it. Again, like continuous flow intersection, Hawk. Don't know how that worked through, but you got to love the creativity. But in the United States, we can't have signals rest at dark. What happens when a signal rests at dark? It becomes an always stop. So it has to be a beacon. So originally the Hawk was actually called a beacon, but what do we call it now? Well, now it's formally called a pedestrian hybrid beacon. That's the origin of the name. So let's start calling them pedestrian hybrid beacons, or PHBs. So let's go back and look at some of these old names here. Gosh, I wish I had invented the word continuous flow intersection, but it's a displaced left turn. It's getting more focused in on what the name is. A super street is really just a restricted crossing U-turn. It's a fancy name. And did you know that the urban interchange was actually originally marketed? There was an engineering company that was going to try to patent and sell that they invented the urban interchange, when really what it is a single point diamond. And as a matter of fact, single point diamonds have been around for a long time. And of course, the Michigan left is a median U-turn. So why it's important for us is to understand the origins, but let's use the correct names so that we can have a conversation with each other. Oops, sorry, excuse me. Finally here, have the courage to say yes. And it's really easy to say no. Probably in your organization, if you're in Caltrans, you feel like, I don't have any authority to say yes. I don't know if I have the responsibility to say yes. I'm afraid to say yes. So if I say no, I can't go wrong. But what you need to do is gain the confidence and learn how to say yes. And I want to let you know that the word, I don't know, this needs more analysis. I can't make my decision. That's just really another way of saying no. And I've been around a long time and I've gone through this. So how do you gain the confidence to learn how to say yes? Well, it's learn fundamental principles. You're never going to find a design manual guidelines that have everything you need in them. But if you can learn fundamental principles, they're going to help you be more confident in applying engineering judgment. Work with your project teammates. If we look at this location, that just these simple diagrams out of the NCHRP report that Bastian talked about yesterday. Oh, it looks like I've got it wrong one, 834. But what's going on here is on the left side compared to the right side are two different variations. But the simple part is that these are fundamental principles of slowing the vehicles at the crossing, increasing the visibility for the distance to the crossing itself, and improving the view angle for drivers. And so while this view angle, this is a diagram showing it as a lane add, many times we used to pull up these diagrammatics or have intersection designs where there's no view angle for the driver. So learn intersection fundamentals and apply those. That's what's going to help you learn how to say yes. Learn new concepts. Are you familiar with protected intersections? They're using design elements to reduce conflicts between pedestrians, bicycles, and motor vehicles. The principles of protected intersection are to minimize exposure to conflicts, reduce speed at conflict points, communicate right-of-way priority, help people understand how to use the roadway, and provide sight distance. Now, do those four principles sound similar? While they came out separately, these are a lot of the same kind of elements as Jerry was highlighting, the roadway design hierarchy, removing the conflicts, reducing the speeds, managing time with our conflicts, or increasing the attentiveness. So this concept of protected intersections is something that's relatively easy to do. And so this is some examples of this. If we look at this is a tight location, probably very urbanized. But what you can see is it's an environment with many users. That truck is turning very slowly, but if you look at the pedestrian facilities, they're separated from the bike facilities. There's a separation between the bicyclists and the pedestrians. The truck that's turning can't right hook the bicyclist who's in the intersection. And here's just, again, a diagrammatic from the MassDOT guide. But what you can see here is we're starting to look at each of the users and design for each user. And for you as geometric designers, wow, look at all of this great stuff that we can possibly do here. And we need to know what size truck that is. We need to make sure if it's an STAA or a California legal that we can cover it. We want to be thoughtful about the environment. And we may not be able to do this in all locations, but I want you to be aware of where this works through. But did you realize that NCHRP Research Report 1043, Guide for Roundabouts, has similar elements in it? And Gina highlighted this, that your Caltrans HDM still references and still uses the principles from NCHRP 672. That's okay, 672 is still really good. This 1043 document really greatly expands on the contents of 672 and provides a lot more information. So here's just a simple single lane roundabout design with treatments for pedestrians and bicyclists. But what you'll see is we're separating out those users. And yet there's another example here at a multi-lane design where we can separate out the peds, the bikes, all of those users. And while we often think about that at the crossing location, if you look on either edge of those roadways, what we're doing is detectable warning strips and looking at the conflicts between the peds and the bikes, as much as the bicycle and the peds and the motor vehicles. So this stuff is around here. Also, what can you do to learn how to say yes is understand precision versus accuracy. So here's our roundabout guide. Here's our typical way we can look at things. You've done this before. You calculate an R1. You pull up the table that's from AASHTO. It's highly impressive because it has funny numbers and diagrams in it. You put that radius in and you compute for the speed and you come up with 30.987 miles per hour. That's what you calculate. Man, that's good. Well, I don't think I can carry it out that far. I'm going to round it up to 31 miles per hour. Okay, well, that's a pretty big move there. But what's the entry speed for a multi-lane roundabout? 30 miles per hour. This is 31 miles per hour. Oh my gosh, is this a fatal flaw? Is this roundabout thrown away? Oh, I don't know. What am I going to do? Well, let's understand where this comes from. First of all, when we compute our speeds, it's based on, well, pick a portion of that 65 to 80 feet in at the entry. Make sure that you're back about approximately 165 feet from the outside edge if I'm using ICD, if I'm using CAD. Let's go ahead and draw that fastest path. Which way do I do it? How close do I do it? We all do it a little bit differently. Okay, so that's how we got that R. Well, let's take a look at our vehicle. Well, clearly every vehicle in the world is 6 feet wide. So clearly when I'm using my offset of 2 feet to a fixed object, it's 5.0 feet. All my curbs must be the same. All my drivers must be the same. All my vehicles must be the same. But the real important part here is, what are the project considerations? Are there other curves in here? What's the environment around it? What's the messages that the land use is telling us? Do we have features and elements up and downstream? Is it part of a roundabout corridor? Is it the first intersection off a ramp terminal interchange where nobody can pick up speed? We need to be able to think about all of the project considerations. Or what's the benefit of this roundabout compared to the other intersection form? So that leads me to this. Don't hold out for perfection. Focus on optimal solutions and how they attain the greatest value for the project. So if we think about our existing condition, what are we trying to achieve and whom are we trying to serve? There's probably some sort of ideal design. Is it nominal approach that Gina was talking about yesterday, where I have to pick a value from our standards? But the key here is we often get so caught up into what's optimal, but what can't I achieve? What's missing? I can't get that standard. I can't get the 500-foot radius. I can only get 450 feet. And we get caught into that, and we're afraid to make a decision, and we don't know what to do. The point here is, let's focus on what we gained. How many projects that were really, really good projects ended up as the no build because nobody could make a decision, because we were looking for the optimum, or excuse me, the ideal, that we had to have perfection. There's a lot of places, even in Caltrans where I worked with you, where a lot of good roundabouts didn't get put into place because back in the day, people were looking for the ideal and following some sort of criteria that was non-attainable. And Gina mentioned this yesterday, and I thought it was great because I had it in mind too. But a roundabout design that is less than ideal could still provide superior safety and operational performance over other alternatives. The point here is, let's see what we can get from the roundabout. Let's not worry about the perfection. So in closing, you are in a fantastic organization, and I'm proud to be able to work with Caltrans. You're implementing, and you get a chance right now to implement policies that support reduced crashes and reduced crashes in total, but severe and fatal. You have the opportunity in your planning and design decisions to save lives and money while you do it. You get to be the stewards of the money around you. And what I say is, challenge yourself with continual learning to gain confidence in making your planning and design decisions. So that's my pitch, and I'm sticking to it. So I'll open it up to questions. John, I hope I get to be invited back some other time. I haven't upset the cart.
Great. Thank you so much, Brian. I mean, you were just so chock full of information on various topics. I mean, you covered technical things, practical design, some philosophical things, and I think really a good challenge to each of us to really be the best engineer that we can.
Planner too.
Yes, absolutely. We all have limited resources to build our projects. So I think he had a lot of things that we could all heed and really improve ourselves. Do want to open it up for questions. So we currently don't have any questions. Is there anyone who is brave enough to raise a hand or anything you want to put in the chat? This is a great opportunity to stump Brian. So if not, no, just want to thank you, Brian. Excellent job as usual. Really appreciate how you really kind of tied everything together, gave us the national perspective as well. So thank you.
My pleasure.
All right.
Thank you.
Thank you. Okay, next online, I think we have Gina Lopez and Bernice Chan from our headquarters division of design. So you could go ahead and start sharing. They're going to talk about how we calculate safety performance, and specifically running the HSM, the Highway Safety Manual. And this is new for a lot of people. It could be challenging, so they'll provide us with some information on how to do that.
All right. Thanks, John. And just real quick, just make sure you can see my screen, no obstructions or anything like that, and hear me.
Looks good.
Okay, perfect. And Brian Ray, oh, not hard to follow at all, right? All right, so yeah, John came to me and had a project in mind that he wanted to use as an example for this, for the ISOAP workshops, and, you know, said, hey, can you help us out with applying the HSM on this example?
It, like, doesn't microwave, and I didn't know if it was the microwave or.
Oh, okay, hopefully I muted that background noise. And so that's kind of what we want to, myself, Gina Lopez, again, if you weren't with us yesterday, I'm from the Office of Project Support and Headquarter Design. So not only does our office house some of the roundabout and other intersection SMEs, but we also house the HSM team for Headquarter Design. And so my colleague Bernice will close it out. But yeah, just want to show you how you would go about the steps to applying the HSM, and then we'll go over an example. So this is what we'll be talking about is the steps, right? The very first thing that you want to verify is what facility type that you're in. So which chapter of the HSM I'm going to use, because that's going to inform all your decisions moving forward. And if you kind of don't understand that or don't choose the right facility type right from the beginning, you may, you know, have to do a lot of rework, or you may have realized I can't apply the HSM the way I thought. And so that really kind of changes the whole strategy on the HSM application. We're going to talk a lot about the limitations that are associated right now with the HSM. The second edition will be coming out later this year, and maybe those some limitations, they'll start to decrease. They'll still be out there, so it's going to be very important to understand how to potentially workarounds for those limitations where we can't apply the Part C of the HSM, and I'll go over what it means when I say Part C. But the Part D portion of the HSM could help maybe fill some of those limitation gaps from the Part C. All right. And our goal in applying the HSM really is to apply it quantitatively, which then translates into an economic analysis, right? Some type of benefit to cost ratio or cost to the state. You're getting some type of value to help with your assessment when you're applying the ISO. Not the only assessment, right? We talked about that yesterday. There's a lot of other things to take into consideration. And then, like I said, I'll hand it off to my colleague Bernice, and she's going to talk about, she's going to walk you guys through an example of us applying the HSM. And then 5 and 6 you see here on your screen, we're not going to go over it just because of the time, but these are very useful slides that just tell you where these tools are located, where the resources are. This is external resources so that our local partners and agencies can also have access to our guidance documents and some of the training. All right, so here we go. We got 4 different parts to the Highway Safety Manual. We got parts A through D. What we're going to focus on today is part C through D, not to say that there's not a lot of good information in parts A and B. So part C is where you're going to have various chapters, and these are going to be your safety performance functions and your crash modifications that work together. And then in your part D, it's all about crash modification factors, and those are separate from your part C, crash modification factors. When the second edition is released later this year, they're actually going to call the part D CMFs. Those will remain the same, but the part C crash modification factors, those are actually going to be called adjustment factors, so that it differentiates the two different types of CMFs. So moving forward, second edition gets released, we say adjustment factor. We know that it works with the part C crash prediction models, and they're different from the part D crash modification factors. Okay, the very first step when applying the HSM is to understand what the part C encompasses, and it's going to encompass chapters 11 through 12, and it also you also have chapters 18 and 19. I just have chapter 19 here on the screen because we're talking about intersections and interchanges. So chapter 18 is all about mainline freeway, right? We're not talking about that today. Again, we're focusing in on our intersection control, our interchange locations, intersection types, all that good stuff. So it's going to be very, very important when you're trying to apply the highway safety manual. Which chapter do I use? Am I in a rural two-lane, two-way road context? Am I in a more an urban suburban type of environment, right? And you need to figure that out. It's one of the very first steps. And sometimes just got another question recently. More times than not, you're going to be in somewhat of this gray area. And the example that we have, that kind of was the case. You're right at this border of a transition area. Got to use that engineering judgment. What's going to make the most sense? So it's not always going to be the easiest. I have this website down here. This website is also referenced in our highway design manual. It's basically to help you out determining whether I'm in an urban or rural type of environment, and then that's going to help us decide which chapter am I going to use, because not every chapter of the part C of the HSM can look at the same intersection types or interchange, like for chapter 19, right? That's going to be a no-brainer. If you're at a grade separated, you're at an interchange, you're going to go straight to chapter 19. So it's really those chapter 11 through 12 where I'm not, which chapter do I use? And that's going to be the first decision that you're going to, that you make. And then you'll be able to tell, you'll from there understand which intersections can these different chapters look at. They're not the same. Okay, and there is there's guidance about kind of determining whether I'm in a rural, suburban, or urban type of environment. But like I said, I would really highly suggest using that link that we have here on the screen. What you see here, it's hard to read, but this is a cheat sheet. I'm not sure if this will be distributed, but we have been distributing these to the districts when we go live. This is a cheat sheet. It lays it out for you as far as which intersection types can each chapter address. So you see here, starting from the left and the top, that's your chapter 10, and that's listing 3ST, 4ST, 4SG. All that is to say is chapter 10 can look at your 3-leg stop controlled intersections, 4-leg stop controlled intersection, and 4-leg signalized intersection types, okay? Then you go down to rural multi-lane highways, you're going to see the same intersection types in there. It starts to change a little bit with chapter 12, and then on the right-hand side, that's your chapter 19. Again, you're in grade separated, you're at interchanges. It's completely different at that point. Something I want to note right off the bat that you won't get from this cheat sheet, right? I highly, highly, highly recommend popping open that highway safety manual. Again, this is a cheat sheet. It's a starting point, but there's so much more detail and so much more additional information that something you won't glean from this cheat sheet is, and it's in very small print, for your 3-leg stop controlled intersection, that's only stop controlled on the minor legs, right? That's not a full way stop control. So all of these little tidbits are very, very important for you to kind of understand, again, what are those limitations? What can the highway safety manual truly take into account? Another thing that you're gonna, note is it shows the control type. It specifically calls out the control type on the chapter 19, but for the rest of it, the rest of the chapters, 11, 10, 11, and 12, there's nothing in here that says yield control, right? Those are roundabouts. Everything is either a stop or signal type of intersection control. And in fact, we've been talking about, which I really like, is the form versus the control type. Well, the forms that you see here, we do not have Part C crash modification factors that are in the first edition of the Highway Safety Manual. They are ready to go and they've been available for the second edition, maybe for the past, I'd say 3 or 4 years, but there's a big disclaimer that says if you're going to use these new crash prediction models for roundabouts, there isn't any for DDIs, but for roundabouts, we do have them. And it says you essentially have to have calibrated models. And right now for California, we do not have, the crash prediction models from Part C are not calibrated. This is based on national data. There was some California data used for the crash prediction models in the first edition. But knowing that the second edition is coming out, that's what we're working on, is calibrating the crash prediction models that will be in the second edition of the Highway Safety Manual. So with that, that's where we're going to have to use the Part D CMS to supplement. But before I get there, I'm not going to go through this slide because essentially the steps 1, 2, 3, and 4 are talking about picking that facility type, because then you'll know which chapter of the Highway Safety Manual you need to use. And then number 2, right, you'll know which intersection types are included because they do differ from chapter to chapter. And then I could look at, okay, my 3-leg, 4-leg intersection control, what can it handle? And, I wanted to highlight one more thing on this slide is the AADT. So our traffic volumes. There are different maximum traffic volumes that are associated with the crash prediction models. And that's off to the right columns of each of the intersection control types. Each of these crash prediction models for the specific intersection types can only handle so much traffic volume. And when I say, what is our traffic volume at this particular location, typically, we should be looking at a 20-year design, maybe something less, maybe 15 years. That's what we want to compare. We want to look at that traffic, that forecasted AADT when we're comparing it to the maximum AADT that these crash prediction models can handle. There is a workaround depending on how much we may exceed the maximum traffic volume that the crash prediction model can handle, right? We got to use engineering judgment. A lot of times there's limitations. And so, hey, let's document that maybe year 15 was when we started to exceed the models. And we're going to continue to use that year 15 forecasted traffic volume for the rest of the 5 years in my design period. Okay. Is that, something that's reasonable? I'd say it depends, but most likely, yes. I would say that's not a cause to completely throw out the Highway Safety Manual and say, well, I exceeded it, because the majority of the years you didn't. So just wanted to highlight that. And so again, this just basically goes over the steps. And number 3 is kind of reminding me to go back because the limitations on the traffic volumes that these crash prediction models can handle can be a roadblock at times. Okay. And then the CMFs are also going to be different. So your crash modifications, your Part C CMFs, each of your crash prediction models takes into account different geometric features and different traffic control inputs. Okay, talked about the limitations and we focused on Part C, but I want to really talk about Part D, the difference of using a Part D quantitatively versus qualitatively. And this is going to help us fill those gaps when we do have those limitations with the Part C models. We get this question all the time of, I don't understand when you're asking me or when you're telling me, are you using a Part D, or, we'll ask, are you using a Part D quantitatively or qualitatively? Because there is 2 different ways to use the Part C CMS. And essentially, again, these are standalone crash modification factors. They are apart and separate from the Part C crash prediction models. That's why they're in a completely different part of the highway safety manual itself. And so we've talked about crash modification factors, all afternoon yesterday, and we're going to continue to talk about crash reduction factors, crash modification factors, excuse me. I think we all realize that these are basically, it's either a countermeasure or it's representative of your change in crash frequency, depending on how we're applying it. And so and there's two main ways, right? Quantitatively and qualitatively. I think the two definitions are pretty self-explanatory. And our preference is to use the Part D quantitatively if we can. But in order for you to apply a Part D crash modification factor quantitatively, you have to have a completed Part C analysis. You have to have an output, right? We're trying to quantify the number of crashes over a time period. And when we have that output from the Part C and we actually have a number of crashes and we're trying to apply a Part D, then we can still use that Part D and still have a number, a quantitative application of the Part D, because we're simply applying it to our Part C output. That may not always be the case, because I talked about the limitations that we have, and we may not even have any output from the Part C, but there's still something where we want to figure out, so there's a proposed change, right? That we know it can't be accounted for with the Part C prediction models. I can't even apply a crash prediction model to this location. So if I don't have a Part C output, then I'm simply going to go to the CMF clearinghouse and I'm going to do a qualitative analysis. And the ISOAP stage 2 specifically says that. A lot of limitations. If you cannot apply the HSM quantitatively, then you can resort to a qualitative analysis. And this is essentially where you're going to go. It's going to be the FHWA CMF clearinghouse. You can see here chapters 13 through 17, they're slightly grayed out. Those are chapters 13 through 17 of the Highway Safety Manual. And they're grayed out because the first edition came out in 2010. I think the clearinghouse was either right after or shortly after. But essentially all of the Part D crash modification factors in the manual itself have been migrated over to the CMF clearinghouse. The CMF clearinghouse, it's a database that's constantly being added to, updated, whereas the 2010 manual, it's stagnant, right? Those CMFs have been in there since the past 15 years. And so we want the latest and greatest crash modification factors. We want you to go to the CMF clearinghouse. And so that's why we have the link to the website here. And many times in our live trainings, I would reference basically that all of the percent reductions in, either the fatal and injury crash severities that Jerry and John and all our good speakers have been talking about yesterday and today, those studies have came from the CMF clearinghouse. Sometimes there will be a direct reference to the crash modification factor report that study came from. And so when Jerry's been, stating the reduction, that's essentially, it's the same thing as a crash modification factor. It's just your CRF is 1 minus the CMF. So when Jerry said, well, roundabouts are showing, up to 80, 90% reduction, basically what you would do is you would say my crash modification factor is going to be about 0.2, 0.1. That's how it works. It's your 0.8 minus your 1 minus 0.8 or your 1 minus 0.9. So CMF less than 1 is what we want. That's indicative of reducing crashes. Okay. It's not the easiest if you're not familiar with the crash modification, the clearinghouse, looking for CMFs. What you really want to find is a crash modification factor that has a good star rating. And Bernice is going to go over this about how we found crash modification factors for the roundabout alternative, because this is where you're going to have to go to find what is the most suitable crash modification factor, and suitable being it has the same before and after configurations that your project or that your intersection has. That's when we say most suitable, most applicable. There's other considerations, but that's really what is gonna help you make the best decision when looking for a CMF from the clearinghouse. Okay, so before I hand it off, this is essentially what the outputs look like when you run your analysis. Before I go into kind of like the details of getting that economic analysis, just wanted to point out that we actually analyze the no-build alternative as part of your analysis. And why do you analyze the no-build alternative or the existing condition? Because you're always going to be comparing. If it's a new intersection, well, then you're going to be comparing your intersection control types, your alternatives, whatever it may be, right? For this particular example, we are going to be comparing against the no build. What is happening out there now? And we're going to apply the HSM, and you can see how we have our total crashes. We have our crashes also broken up into crash severity, which the tools will do for you. That's not something that you have to worry about doing. But the point being is we applied the HSM to the no build because we're going to compare the alternatives against that no build. How are they performing predictive safety wise against the no build alternative? And you can see alternative A, it's actually reducing those crashes, which is a good thing. That's not always the case. And it's very, very prudent that you understand what these crash prediction models are actually taking into account so that you can explain, well, why are my crashes increasing, right? Is this a bad project? Probably not, but you need to understand what the models are taking into account so you can understand why those crashes are increasing. What we'd like to see mostly is hopefully only the PDOs are going up, but if not, again, it's understanding what the crash modification or what the crash prediction models take into account and being able to explain why we have an increase. Something else I wanted to point out is because we're comparing, if I can't apply the HSM quantitatively to either the existing conditions or to, or if I can't apply it across the board to all alternatives, then I'm not making an apples to apples comparison. So that's very important. We get that a lot, especially when you're new to applying the HSM, is I can apply it quantitatively. I have no issues with this particular configuration, alternative A. But I start to get into trouble as I look at some of my other intersection control types or my other alternatives. I can't apply the HSM quantitatively. What do? At that point, you have to make the decision, then I'm probably going to go the more qualitative analysis because I can't do it quantitatively across the board, across all alternatives in the existing condition. So I won't have, you know, the same outputs or the consistent outputs that I'd like to make that comparison. So that's very important as well. But before I hand it off, essentially, this is what our goal is to apply the HSM quantitatively. You're trying to get that BC ratio right. The cost is the alternative business as usual. That's nothing different of us coming up with the capital cost of a project, right? We're not taking into the support cost. We're taking into the actual capital cost. And it's the safety, the benefit. That safety benefit is what is new, right? But that safety benefit is hopefully those crashes reduced. And we're able, with an economic analysis tool that headquarters design houses, to use the actual crash costs that are specific to California. And that's how we're able to convert the reduction in crashes to a monetary value so that we can compare the cost of the alternative or the intersection control compared to the safety benefit that this certain alternative intersection control offers. That's how we get that 1.54 that you see on the screen. So with that, I think, John, you're gonna quickly introduce the example here, and then Bernice will walk you through how we actually applied it to this specific project for ISOAP.
Yeah, so I just want to set up this example. This is in the city of Modesto, which is about 35 miles west of Fresno. And this is a roundabout that's actually under construction right now, but we chose this location as a test case for ISOAP and the HSM. So it was actually run under ICE, but as an exercise, we wanted to apply the HSM to it. So at this location, the city received a CMAQ grant to build a roundabout at the intersection of two state highways, 180 and 33. These are served as the main streets for Mendota, two-lane conventional highways. There's about 16,000 vehicles entering into the intersection every day. So that's well within the realm of a single lane roundabout. So the idea was to realign the intersection, the junction to McCabe. McCabe is this access to a residential street, also provides access to a school. You have a fire station right at the corner. And just to kind of clean it up, we wanted to create a four-legged intersection. And there's a lot of costs involved, but at the time there was enough money with the grant and other sources of funding. Next slide. So this is the other alternative, which is a four-legged intersection, just very typical. Next slide. So what happened was the city got cold feet about putting a roundabout just because of a lot of controversy. The nearby city of Kerman built a roundabout and it created a lot of uproar. And the city decided they didn't want to build the roundabout anymore. They want to put a traffic signal, but that wasn't a project that we necessarily supported. So it just kind of was on pause, on hold. Eventually, the makeup of the city council changed and they want to proceed with the roundabout again. So in-house, we started working on a PSR and looking at the ultimate 20-year design, which is the previous slide, which just had a very, very big footprint impacting that parcel if we were going to realign. This was no longer a viable alternative just because it was just too expensive and beyond what could be funded. So we wanted to kind of backtrack to the next slide. And ultimately, we settled with keeping the current junction, placing the roundabout, and it's going to be a single lane roundabout. It wouldn't quite have a 20-year design life, but fairly close. We think it's going to last 15 years or so. So when you look at future calculations, theoretically, we should be looking at maybe a 15-year design life. But this is a project that can be built. So it was actually awarded for $3.1 million less than engineers' estimates. So how we address McCabe is we do a three-quarter movement. You cannot make a left out of McCabe. So you just make a right turn, go through the roundabout, and this is how you head north to go to City of Fireball or points up north. We worked very closely with the fire station, and they do have access coming out of McCabe to go over a mountable island. So they were happy with that solution. Okay, so I think I could pass it to Bernice to go through the details.
Okay, thanks, John. So we're going to step through the process of how to screen the alternatives that John had mentioned. We're not going to go in depth with the HSM analysis though, because we don't have the time. But what you see here on the screen, it's the no build condition or the existing condition. And we've determined that this project is located in a suburban environment. So that points us to use chapter 12 of the HSM. And maybe you can see it's a little hard, small, but the existing intersection controls for both at McCabe and Derrick Avenues are three-leg stop controls. And HSM classifies this intersection site type as a 3ST. And then for the purposes of this example, we will run the analysis over a 20-year design life. And we have design years spanning from 2026 to 2046. Next slide, please. We've also obtained the AADTs for, well, we have it for the current year, but we really need it for the opening year and the opening year plus 20. Because the AADT is one of the independent variables, and we need to check whether the AADT numbers lie within the applicable limits. And so, as you can see here on the screen, we've obtained the AADT numbers, we've checked it against our cheat sheet, and it looks like we are in the limits. So we've decided we can proceed with HSM analysis for the existing condition. Next slide, please. So we're going to go through the same exercise for alternative A. Alternative A is the signalized alternative. And again, we're in the same location. So we're going to use chapter 12 for our SPFs. And in this configuration, the intersection at McCabe is being converted to that new four-legged signal controlled intersection, but the intersection at Derrick Avenue is being eliminated. So here we don't have one intersection to worry about. And the HSM classifies the four-legged signal controlled intersection as a 4SG. And of course, we'll run it over a 20-year design life. Next slide, please. And then again, same exercise. We're going to compare the AEDT numbers against our cheat sheet, AEDT applicable limits. We're checking it against the Chapter 12 4SG facility type, because that's what we're going to use. And looks like we are within the limits. So we confirmed that we can run the HSM analysis for alternative A. Next slide, please. So let's look at alternative B. And so same thing, we're in the same facility, place type, environment, facility type. So we're using chapter 12. We're also going to run it over a 20-year design life. For this particular alternative, we are dealing with, two intersections here. The proposed intersection at McCabe is a three-legged stop controlled with the added feature, as John had mentioned, or the constraint of a right in, right out configuration. So we're limiting that left turn movement out of McCabe. And also the proposed intersection control type at Derrick Avenue is a new roundabout. And so these intersection control types are more complicated than what we can immediately find and pick out from the available intersection types within chapter 12. So as Gina had said before, when we encounter something of this situation, we would have to explore other options. Next slide, please. So as we recommended earlier, when we hit a limitation, relying solely on the Part C models, we may have to turn to Part D CMFs from the clearinghouse. So just want to point out that, please be aware that when you're searching and entering keywords for querying within the clearinghouse database, it can be a little tricky and it takes some time to get used to and become proficient with, like what Gina had mentioned. Shown here on the screen, we found two CMFs that best match what we're trying to achieve here. The first one has an ID of 9821, and its description is install right in, right out operations at stop controlled intersections, and has a value of 0.55. And we also have we found a second CMF ID number 236, and that description is convert intersection with minor road stop control to modern roundabout. Again, when we queried this in this CMF clearinghouse, we didn't put all those words in. So we, picked out specific words, try to put that in the query and see what comes out and go through it. So with anyone who's not familiar with the clearinghouse, when you search and query terms and words, it may kick back a lot of different results. And some of those may come from different parts of the world. And you may not want to use the European ones because our context is different than theirs. So it does take some time. It takes some patience to sift through them to find the best match. And that may include, reading the available background research that the CMF has, and it may describe research assumptions, the conditions, and environmental contexts of that research. Like Gina mentioned before, the star rating is important and indicates a certain level of quality of confidence in the results. And if you want more information about what all these terms mean and how to read them, please go to CMF Clearinghouse. They have more information and descriptions on all the different terminology that they use. And so we want to go back to this particular example. On the screen, we're showing a summary of each CMF that includes all the features and conditions. And we went down the list and we checked our project site conditions, whether those align or deviate from the conditions of the studied CMF research project. And you'll see that we've put green check marks next to conditions that are similar and red X's for those conditions that are different. Ultimately, you do have to use engineering judgment to determine whether a particular CMF has enough similarities to justify incorporating it and using it in your analysis. For instance, on the left-hand side, we have the right-in, right-out CMF, and we have indicated that with the red X, that area type, road division type, minimum number of lanes, that this CMF is based off. It doesn't match exactly our project set conditions. But we have looked through a lot of the CMF through the database, and we looked, and upon evaluating all those other ones, we have decided to settle on this one as the one that best matches our project. And at the end, we feel that there are enough similarities, and even for the features that are not matching exactly, we feel that the deviation is not too off base, and we're still able to use it in our analysis, and we are better off still incorporating into our analysis than not. Next slide, please. So now that we've determined which CMF to use, our next step is to decide on the approach of the HSM analysis. And then with that, we can finish off with our AADD check. So for alternative B, this alternative, at the McCabe intersection, our approach is to multiply that CMF, that right-in, right-out CMF that we found with the value of 0.55 to the results of the proposed 3ST configuration. And likewise, at Derrick intersection, our approach is to multiply that roundabout CMF that we found with the value of 0.68 to the results of the existing 3ST configuration at that intersection. And since we are utilizing the 3ST intersection model from chapter 12, we're going to check our project AADT numbers against the 3ST and AADT ranges on our cheat sheet. And ultimately, they fall within the limits. So yay, we can run our HSM analysis for alternative B. Next slide, please. So we're going to skip through the details of actually running the analysis. Once you have all your results from your analysis, and they can be done through spreadsheets, and these spreadsheets are free to anyone, and you can download them from highwaysafetymanual.org. Use those to run your analysis. And then after you get your results, it's really good practice to compile them in some sort of organized manner, in this case, such as a table. So it's easy to understand where all the numbers came from, and it's easy for us then to be able to apply the economic analysis to it. The next slide, please. And so you would turn in all your crash prediction results and any other piece of relevant information, like the project cost and any backup calcs to the district, and maybe in turn, if you're a district, then you would turn it into headquarters, Office of Project Support, which is Gina and I. Then we would be able to run the economic analysis using our tool that Gina had described earlier, in order to calculate the total crash cost, and then be able to provide you with that BC ratio. I know I went through that fast, but I think unless Gina has anything to add, I think we can. I don't know if we have time for questions. I do know Jerry's coming up after us, and we have 5 minutes left for this segment.
Hey, there's actually a question I would like to address from the chat, and it's, where does the CMF clearinghouse get their values from?
Okay, good question. I want to come back to this slide. But yeah, I'm gonna go back to the CMF. And they come from all over the world. They come from researchers. They come from, I'm not sure if there's NCHRP studies, but essentially anybody can propose their results and their research to be uploaded in the clearinghouse. But it has to be vetted through. I'm not sure their process of how they actually get approved to be in the CMF clearinghouse. But like Bernice was stating, there's a ton of information on how they come up with the CMF, with the star rating. And they tell you, they give you of information on how they give certain weight as far as how many sites did they have, how many years of data did they acquire, and then the type of analysis that they did. So yeah, they come from all over, but there's a vetting process to get your CMF uploaded into the database.
But the most important part of this is that they come from project evaluations, before or after project studies, right?
Correct, but I'd have to go into the star rating to see if yeah. And then that's what's important, right? When we talked about does the CMF, how it was developed, like Jerry was saying, as part of the actual real life application when they developed when they were getting their data, does that match your before and after of what you were doing? And then John, I don't know if there's any more questions and how much time we have. I think the only thing I just wanted to maybe slightly expand on is, I don't know if anybody caught that for the write in, write out CMF, we applied it to the proposed intersection configuration at the top intersection here at McCabe. For the roundabout CMF, we applied it to the existing 3ST, right? And we applied it, the CMF, the roundabout CMF to the existing intersection because the CMF said convert, right? Stop controlled intersection to a modern roundabout. So what I did was what we did is we took that CMF and applied it to that existing 3ST outcome, because that's how the CMF was developed. It was based on converting an existing stop controlled intersection to a modern roundabout. For this particular instance, applying the write in, write out CMF to the proposed, something that that I don't think we talked about was another addition to this project, and it may be easier to see it on a bigger scale, was they implemented a left turn pocket from your main line onto McCabe. If you're not familiar with what the HSM can take into account, then you don't even realize that that's a change that happened from your existing to your proposed condition that the HSM can account for. So we need to rerun that analysis for the proposed condition, because that's what we want to multiply our write in, write out CMF to. We want to multiply it to the proposed condition because there was additional features that the CMF can account for. If you're going to strictly go to the spreadsheet tools without understanding what you're actually inputting, you will make those errors because you're not familiar with all the background and what you're actually telling the tool, what you're actually telling the crash prediction model. And you could either over account for things, over account for the safety benefit, or you can under account and cut yourself, you're going to cut yourself short. All right. Any other, John, I guess we could answer them via the chat.
Yeah, there are some questions in the chat and also in the Q&A box, but for time reasons, let's go to Jerry. He has a little bit more to talk about safety performance, and then we'll see if we have additional time after that for additional questions.
Okay.
So Jerry, it's hand it off to you.
Do you want me to drive it, Jerry, or you want to run it?
Whoever's in control right now, please continue.
Okay.
Yeah. And I lost my screen, so give me just a minute here. Okay, I'm back. Very good. Okay. So what I am going to cover in probably the next 10 to 15 minutes is a methodology for calculating the collision cost savings, which is the benefit that we get from implementing mostly safety improvement projects and other projects. But this is specifically a methodology that was kind of created back in 2013 when ICE was first adopted. And this tool was created to help us calculate the benefit cost ratio and the collision cost savings for control strategies. And I want to mention also that this methodology is currently being used by the local highway safety improvement program. So all local agencies that submit applications for safety grants that involve roundabouts in particular, they use this spreadsheet tool, which we call CCA or collision cost analysis. And actually Caltrans is currently using this same spreadsheet tool to develop the crash cost savings and benefit cost ratio for roundabout proposals on the state highway system. Okay, so this is it's as an extension of the Caltrans safety programs methodologies. It's as performance-based as you can get, and it is based specifically on Caltrans crash data at intersections across the state highway system. So what I'm going to give you is an overview, and looking at this first sheet, you can see that there's a sample of a worksheet. This is what you see when you open the Excel spreadsheet form. And of course, this is a completed version, but just want to let you know that this is divided into two halves. And about the top 2/3 is locations, boxes for inputs. And then the bottom, of course, is the results that come automatically once you've completed inputting all the data. Next slide. Okay. So this is a blank version, the top half of the form where the inputs are put in. As you can see, there's two types of boxes here for the user to enter, but also some of these are automatically populated. Let's just go to the next, and we can start to look at what this would look like. This has got the data entered for a specific location, fictitious, as you can see. Route 101, 1001 does not exist. But you can see the data is entered specifically for the location, of course, county or post mile, for the area type, rural, suburban, or urban. So the user has to enter that. And then the rest of the information, service life, number of years for analysis. In this case, for roundabouts, 20 years is always used. And then volumes in terms of ADT for mainline and cross street. And these are for both the existing ADT, but also for future year conditions as well. Most importantly, we have the crash data that is entered kind of in the right half lower part. And as you can see, you end up having a number of total collisions, number of injury and fatal collisions. Some of that gets populated automatically. The only thing remaining to be entered here are the cost estimates for the alternatives that are under consideration. So this is for, again, what we're looking at here are control strategies. That's the limitation of this tool. And it has a single-lane roundabout, a two-lane roundabout or hybrid, and then traffic signal and always stop control, those being the most common improvements that usually two-lane or two-way stop control intersections are converted to these types of improvements for safety improvements. So let's go on to one more slide. Okay, so here is the bottom half now. So that was the inputs, and once that is done, they automatically populates the bottom third here, which again, I just want to run this past you. I did say that we inputted the construction cost estimate, I think, on the upper slide or the private slide. That is both the construction cost estimate and the right-of-way cost. Each has to be entered. So now this is a close-up look at, for this example proposal, you can see single lane, two lane, and new traffic signal all were proposed as alternatives. And so you get on the right-hand side here, you get the outputs, which are, there's two outputs provided, automatically calculated the projected savings. Now, this is the crash cost savings or the safety benefit in terms of those are in thousands of dollars. So that would be for instance, the single lane roundabout, $36 million is the projected savings over the life of the project. And that gets based on the cost of the roundabout, I believe it was $10 million was entered. The benefit cost ratio would be 3.64. Now, of course, Caltrans has been using this for state highway projects, and we multiply by 100 to create a safety index of 364. So let's jump down and we'll look at quickly the two-lane roundabout alternative here. Was about $12 million, I think, and you get a lesser, of course, benefit cost ratio, 2.82. What's most important, though, is looking at the next number 3. Row number 3 is the new traffic signal alternative. And I can't remember, that was a lower cost. In particular, I think it was only $3 million was the cost estimate, no right of way, for the signal alternative in the inputs. And you get two things here. You get a projected savings now of $15 million or $15,661,000 is the estimate. And of course, because of the lower construction cost or installation, it's a higher benefit cost ratio of 5.22. Okay, so very straightforward. We're getting two outputs that are both very important. And there's been a lot of emphasis in terms of practice at Caltrans and elsewhere on the benefit cost ratio. But I want to point out that we need to be, when we're looking at ISOAP studies and we're completed with the ISOAP, and now we're looking at entering the selection process, or the project development team would be doing that. Let's go to the next slide. And here is, I want to point out the importance of the benefit, the crash cost savings. So as you can see here, we have important outputs, and they're different for these two alternatives. So let's look at the roundabout. Again, I think I mentioned that the cost savings is 36 million, which is much higher than for the traffic signal. Okay. Now, on the other hand, the benefit cost ratio is much higher, or not, it's higher for the traffic signal, 5.22 versus 3.64. So in some cases, people might look at this and say, well, we want that higher benefit cost ratio. And that is actually in some cases, it could be the right decision. In some cases, you'd have to ask yourself, well, what is the purpose of the project? And the projected savings in this case, the crash cost savings, is actually, for many projects, and especially safety projects, is actually the objective or the goal is to get a higher crash cost savings, or that comes from a reduction in crashes, the estimated reduction in crashes for that countermeasure. And the reason why this is showing a huge difference favoring the roundabout is because the roundabout is actually more effective at reducing severe crashes and total crashes. So this is what we need to be looking at, taking this into account. Even though we have a higher benefit cost ratio, we have a higher performance benefit, which, if you think about the safe system approach and our Vision Zero goal, we're trying to reduce more severe crashes. And that's what this cost savings is telling us. The benefit cost ratio is very important. It's the value of the project, the return on investment. And it's still a good project. It's still a good alternative. But in this case, we're seeing that the roundabout would be a better investment, even though it costs more, even though the benefit cost would be lower. So again, the question to ask, as the ISO process guide is telling us, is that the selection of the preferred alternative needs to be consistent, aligned with the safe system approach, and what is the goal actually for safety. Let's go one more slide. Okay. Ordinarily, if we had more time, we could talk about where this stuff comes from, where these outputs come from in terms of the numbers, the collision cost savings. And time doesn't allow it. It is rather difficult to explain. There's always a black box that does these calculations. What I would say is what's most important to consider here is based on all of the data, substantial data that we have been collecting along the state highway system, crashes at every intersection, and that being categorized into different types of intersections, different control strategies, different environments, which are urban, rural, suburban, even the geometrics of the actual locations. There's subcategories or rate groups, and there's a lot of algorithms and cost comparisons happening in here. So it's extremely data driven, and it's all on Caltrans crash data. So we're getting results we've relied on in our safety program for decades. So this methodology is giving us, as much as the data in the tool and the crash costs are updated, this is a good estimate of what we're going to get with these different alternatives. So I think I'm going to stop there and see if there are, if anyone has any questions.
Very quickly, Jerry, there's a question about where could someone access the CCA worksheet?
Well, every district has had these over time. And I think, John, if we haven't done it already, we're going to have to maybe put this, our next speaker could help us by posting this on the homepage for the ISOAP Technical Assistance
Sure.
Program.
Okay, so this is something that will get posted on the Caltrans ISOAP website.
Yeah, and I think every again, I think the Division of Local Assistance is another location where this may be able to be accessed.
Okay, great. All right, thanks, Jerry.
You're welcome.
And let's move on to our next speaker. This is Lillian Wu. She is the branch chief of the Transportation System Analysis branch, if I got that right. So headquarters traffic operation, and it's actually Lillian's office that owns the ISO process. So Jerry and I are going to be fading into the background after this workshop, and it's going to be Lillian's office that's really going to be taking charge of ISO going forward. So I'll pass it on to you, Lillian. I know you're going to be sharing your screen.
Yes. Let me see. How can I share?
Yeah.
the
And I know you're going to be
right
saving a little time in your presentation. So right after your presentation, we will have a 10-minute break, and then we'll have our next session at 3 o'clock or shortly after 3. But yeah, your screen looks great. Thank you, Lillian.
Okay, awesome. Yeah, hello everyone. This is Lilian Wu from the Office of Mobility and System Performance in the Division of Traffic Operations. So my session will talk about the operational analysis needed for the ISOAP. So how to calculate those mobility performance, what level of analysis is needed for which stage, and how to do it. As you might know, the operational analysis part majority is still the same as the ICE requirements. So this session will focus more on the DPHD, stand for Daily Person Hour Delay Metric Calculation and Analysis. Okay, cool. Let's jump in. So first of all, let's quickly review the two stages that has been covered in yesterday's session. So stage 1 of the ISO provides initial screening of strategies, mostly qualitative level assessment to determine the insurmountable constraints and eliminate the infeasible strategies. The constraints can be environmental, right of way, but for operational analysis, stage 1 focus more on the capacity constraints for all the alternatives. When we get to stage 2, it has more detailed and quantitative assessment for the most viable strategies from the stage 1. So specifically, we're talking about step 2.2 here. When we do the most detailed operational analysis using various of software tools for signal intersections, options or synchro, sim traffic, Vestral, they both are based on having capacity manual methods. Each have their strengths and their weaknesses. So pick that one applicable for your project. CJOY is the one we use most for roundabout analysis. For more complicated intersections such as diverging diamond, interchange intersection, or displaced left turns, or other configurations like Jerry covered yesterday, micro simulation like Vism can give better performance evaluation. So we also talk about the step 2.5 here when we need to calculate the benefit cost ratio, which involves operational analysis to calculate the delay saving benefit. Okay. So what we have talked, stage 1 and 2, those are the typical requirements for each stage. Generally, as shown in this table 1 from our ISOAP guide, the delay analysis are for stage 2, although recommended as early as possible because it's somehow relevant to the capacity analysis as we mentioned for stage 1. I want to get the first key message here. If your project is expected to use SHOP funding for the OI program, means Operational Improvement Program 310, the operational analysis is required to calculate the DPHD in stage 1. Here is why. The DPHD, daily person-hour delay, was adopted by Caltrans Asset Management as the performance measure for SHOP OI projects last year, which requires the DPHD saving to be reported during the PID phase in order to get the project programmed. So the project cannot be programmed without this DPHD saving estimates. SHOP program projects are very time sensitive, and we saw some projects missed the window due to lack of delay analysis in the PID phase. So that's why I want to emphasize these requirements in bold here. Remember that SHOP projects do need some detailed level of analysis during the PID phase, which is the stage 1 for our ISOAP program. They're kind of overlapping here. This was not included in the ISOAP guide because they both released last year, similar time. So please be aware of this change. And we do have a spreadsheet tool to do the DPHD calculation, and I will talk more about it next. But before we do that, just want to show a figure to show the time sensitivity for SHOP project programming. For the 2026 cycle, we are approaching the deadline around the end of June 2025, and we have some intersection improvement projects reviewed and programmed successfully. And we did see the challenge when a project doesn't have the analysis or the input data needed. So that's why we feel it's important to share this message to make the next cycle, the process smoother. So now let's get to our spreadsheet tool about the DPHD analysis. This is a very quick example that to show the Excel tool we developed in compliance with the DPHD guideline. The no build here is always stop control. The build here is roundabout, but you are free to change this according to your alternative, because the key here is to compare the delay between the build and no build. So please note that the DPHD analysis is only required for opening year during the PID phase. This might help you to better plan for your resources. And next, we'll take a closer look at what the input data will be needed for this calculation. We have the volume data, both existing and opening year AADT. We need the traffic benefited percentage, which is typically 100% for intersection study. We also have truck percentage, the average vehicle occupancy, AVO, which is used to convert the vehicle delays to person delays. So the guideline has some default value for your use if you don't have project specific numbers. We also have transit and pad bike information. Depending on your project type, locations, and purpose, you might not have the relevant information, but you might. So those two can be optional. So in addition, you will also need to forecast the peak hour volumes for the opening year based on existing counts and apply a growth factor. We need to document the sources of the applied growth rates. Sometimes we saw super high growth rates like 5 or 10%. Then you might want to double check and make sure it's justified. Last but not least, the tool also asks for the delays for both no build and build. Note that this is for intersection level delay, not the worst moment delay, even for two-way stop intersection. Okay, a quick sum up for the stage 1 or PID phase operational analysis requirements. If it's a shop operational improvement project, please document your input data sources, submit the analysis files for headquarters review. Once it's reviewed and concurred in our system before the deadline, the project can be programmed for next shop cycle. Okay, next, let's talk about the stage 2. So the delay benefit calculation for benefit cost ratio analysis, which is one component here under the performance-based analysis metrics in step 2.5. Previously, I think Jerry just shared about the collision benefit calculation in their tool. So this one is similar, but it's for the delay benefit column. Yeah, okay. So operational analysis is also needed to fill in this delay benefit column based on DPHD saving, which considers the operation cost for the whole project life cycle, typically to 20 years after the opening. We also developed the Excel tool earlier this year to do this calculation. We'll go through some key snapshots here from the tool. Here we're saying is the travel time values. We updated these values for automobile, truck, pad bikes separately based on the most recent data from 2024. So the older tool, you might see some old numbers. That's one update we did. So the tool looks very similar to the DPHD analysis tool we have talked earlier, but it includes some adjustments for BC calculation purpose, and it includes both the opening year and the design year to cover the whole 20 years after opening. This is a snapshot for opening year, and the next one, this is for the design year. Please note that you will need all the inputs as we talked for opening year analysis to do the same for the design year analysis, such as AADT and peak hour volumes for the design year, intersection delays using Synchro, Cedro, or other analysis tools as we talked earlier. Here we show the inputs for BC calculation. The delay benefit from the opening and the design year calculations are linked to the earlier tabs we showed, and you can change the other parameters here, such as the project life, applicable days, and the project cost based on your projects. Note that the 250 applicable days here is assumed as the 250 recurrent weekdays in a year. Probably a good default number for your use, but you can also change. The total delay benefit will be calculated by the Excel tool. And more specifically, the total delay benefit is distributed through 20 years in this example, based on a discount rate of 4.9% and a compound annual growth rate for about 6.2%. So as a summary here, also on the left shows the key inputs and the results on the bottom. That's where you want to pay attention in the tool. We haven't officially published this tool yet, but you can reach out to the district coordinator, ISOAP coordinator, if you think this is helpful for your project. Okay, I will end my session with a recap on the key messages as we discussed. So for the ISOAP stage 1, during the pre-bid phase, think about the input data needed for DPHD analysis if this project is expected to use SHOP funding. During the bid phase, in addition to the 8 steps we have talked about, DPHD analysis is also required for SHOP project under the program 310. For all other projects, stage 2 is when the detailed operational analysis is needed. We covered the DPHD calculation and the delay benefit saving based on DPHD saving to complete step 2.5. But in addition, stage 2 is also where we needed to conduct more detailed analysis in for additional considerations, such as more performance measures about the delay, the queue lengths, the volume capacity ratio, and we might also need to focus more on the worst or key moments, look into the potential queue spillback issues. Next is to comply with the variant standards requirements, as we always do. And last but not least, the adjacent intersections, right? ISOAP mostly focus on a single intersection, but if there are closely spaced adjacent intersections, you might need to include them in the analysis, make sure things like the signal coordination works, the queue storage works, so overall to deliver a successful project. Okay, I think I'm right on time. Thank you.
Thank you, Lillian. So we have time for one question, and we do have one question. Where can we find the DPHD spreadsheet?
Okay, yeah. I think we posted on the ISOAP website, but if you don't find it, you just Google ISOAP. We have an external website for our ISOAP, right? You should be able to download from there. If you don't find it, reach out to the district ISOAP coordinators. We have spreaded it already. Yeah, good question. Thank you.
Great, great. Thank you, Lillian. Okay, so thank you for getting us right back on time. So at this point, we are going to take a 10-minute break. So please be back at actually 3:01. During the break time, we're going to show a video about installing a temporary roundabout. So feel free to view that if you so choose. Otherwise, we'll see you all back in 10 minutes. Okay,
Thank you.
so yes, yeah, and I'll introduce you, Mohammed. So the next topic is about pavement. So there's been a lot of concern about the high cost of concrete pavement, which in a lot of districts has been recommended for roundabouts, and a lot of times that has been just cost prohibitive to actually go with concrete. We know it's the preferred, but we just want to dive a little bit deeper and ask: is it actually okay to use HMA? Are there certain cases where we can use HMA, and what are the pros and cons? So we asked our District 6 materials engineer, Mohammed Al-Asi, and he gave this presentation at the District 6 in-person workshop, and had a lot of good information that we wanted to share with the other districts as well as our external partners. So yeah, thank you, Mohammed.
Thank you, John. Thank you for the introduction. Absolutely, yeah. Part of the reason why it's usually preferred to have concrete pavement at roundabouts is because flexible pavement is associated with some types of pavement failures and distresses. If you can go to the next slide, please. So there are two main common distresses that we see at intersections in general and roundabout. The first type is pavement rutting, and really there are two types of pavement rutting that we encounter, and it's very important to distinguish between the two so we can mitigate those types of failure. So the first type is the surface rutting. This type of depression on the surface of the pavement is caused by a soft asphalt binder or a soft hot mix asphalt using a soft binder grade that will deform under heavy traffic loads and high temperature. So due to the nature of intersections and roundabouts, traffic move at slower speeds. This is because asphalt is a viscoelastic material, so it's time dependent as well. So the time of loading will affect the damage caused to the pavement surface. So when you move at a higher speed, you will have less damage, while when you're moving at a slower speeds or when you're stopping completely, you will experience more damage to the pavement. The second type of rutting is subgrade rutting, and this type of depression of the pavement is carried throughout all the layers of the pavement, as you can see on the right hand side of the sketch here, cross section. It goes all the way down to the subgrade, and this is usually due to inadequate pavement structure. So we don't have enough thickness of the pavement structure to carry or handle the design traffic loads. The next slide, please. The other type of distresses that we often see or observe at intersections and roundabouts is pavement shoving. So this is a permanent deformation of the pavement surface, and this type of pavement failure is caused by traffic or heavy trucks when they are braking as they are approaching the intersection, and when they accelerate either they slow down and start to accelerate as they leave the intersection, or when you have a signalized intersection, when that signal turns green and the traffic starts to accelerate. So at the approaches within like 200 to 300 feet of the approach of the intersection, you would see this type of pavement failure. This is caused by many factors. Mainly the stability of the HMA is the main reason. We have unstable mixed design. And this is where materials engineering here comes to select the right material type to be able to withhold the type of traffic movements near the roundabout. So special considerations should be taken near intersections and roundabouts. Next slide, please. So here I just want to get an overview. I don't want to get into details, just of what type of studies we do before we can decide if flexible pavement would be appropriate at a roundabout or at an intersection. We do a lot of review of the intersection history. If this intersection has had experienced in the past these types of pavement failures, what type of basement soil we have, what is the expected traffic throughout the design period of this project, and what percentage of that traffic is truck traffic. So all of these are factors that plays a role when we select the pavement material. So next slide, please. Okay, we can select from 3 types of pavement structures. The first one is rigid pavement. It is the preferred alternative at intersection, as I mentioned earlier. It comes at a higher cost. If the cost is if we have the right fund allocations, it's the preferred cost. It minimizes maintenance needs, so it will like reduce the need for our staff to go on the field to make repairs to the pavement if there's any types of failures. So it will have a longer life as well. So we designed a rigid pavement based on the Highway Design Manual, chapter 620. And we have options to design as either jointed plain concrete pavement or continuous reinforced concrete pavement. In a roundabout scenario, we have received some feedback from our maintenance partners that CRCP is preferred as when we have JBCB, sometimes slab replacements put them at a higher risk in the field while they're trying to make repairs to those individual slabs. Okay, next slide, please. So the other type of pavement is we have a flexible option. So the comparison between rigid pavement or flexible pavement should come after a life cycle cost analysis is performed. Also, I wanted to highlight that at a roundabout, maybe HMA is more suitable than at an intersection, because traffic, when they are approaching the roundabout, they do not come to a complete stop. They usually slow down and they move throughout the roundabout and leave it. But the caveat of that is also like we have the turning movement that will cause the pavement to shear as the vehicles are navigating through the radius of the chicanes of the roundabout. So it should be a balance there. How do we design flexible pavement to withstand the traffic at this intersection? Basically, we select a stiffer asphalt binder. So selecting a stiffer binder will allow us to avoid any surface rutting, as I showed in the first slide, due to the lack of stiffness or having a soft asphalt binder. So we have recommended those special types of asphalt binders at these locations to withstand the high volumes traffic and at high temperature areas. We designed the roundabout for either 20-year design life or 4-year design life, and the final decision is based on life cycle cost analysis. And also we take into consideration some safety concerns as well. Like we want to reduce the time that our maintenance, field maintenance will be exposed in the field. Next slide, please. All right, so the third type of asphalt pavement that we recommend, this is limited to intersections that have a lower volume of traffic. We call this a short JBCB concrete overlay over asphalt. So when you have an existing intersection that has a low volume of traffic, usually the average annual daily truck traffic is below 2,000. We can utilize these by removing the top layer of the old hot mix asphalt and white topping it with concrete pavement. And this topic can be referred to in the table 623.1 in the Highway Design Manual. If you can go to the next slide, please. All right, so the way this concrete overlay works is I have two cases here. Either we have a melon overlay option, or we can do a pavement recycling, either a full depth recycling or a partial depth recycling, and then applying this concrete overlay. So in the first case, if we have an existing HMA pavement and we would like to mitigate the risk of pavement rutting or shoving at the intersection, we can mill the top layer of the asphalt, providing that the existing asphalt is in a good condition, meaning that pavement cracks are only limited to the top surface of the pavement. So we can do a milling of the top layer, 0.3, 0.4, depending on our thickness that we select, and then do an overlay with concrete pavement. And this is will be a short slab, which means it's 6 by 6 foot in dimensions. The other option, when the existing pavement is in poor condition and we would like to design the roundabout to withstand the traffic of this roundabout or intersection, we do what we call is pavement recycling. So we can have a milling machine that would recycle the entire thickness of the existing asphalt concrete and part of the base as well. Then this is done either through foamed asphalt or concrete binders. And then we can do the topping with the concrete overlay. And this type of pavement design, really, it's limited to shorter design lives. So we don't expect it to last for 4 years, for example. It can be limited to 10 to 15 years before another rehab is needed. Next slide, please. I just want to show another case study. This is a project that was done using the short jointed plain concrete pavement with the Texas DOT. They have this completed construction in 2012. And these are some images from the last year, which shows that the pavement is holding up pretty well. You can see on the right image here, the concrete is limited to the intersection area. After that, it will transition to a flexible pavement with the hot mix asphalt. That's all I have for you today. If you have any questions, let me know, please.
Yeah, thank you, Mohammed. Lot of really good information that you provided. So one thing I just want to mention is we really want to minimize our workers on foot at roundabouts, particularly in a circulatory roadway, because it takes a lot of effort for a lane closure within a roundabout. You potentially need to have flaggers at every single approach. So that's one reason why our maintenance staff, they really want to have this pavement that's going to last a long time, that they're not going to have to be out there filling potholes. And I think also the amount of truck traffic really is going to affect on what type of pavement we want to go with. You know, obviously with a lot of truck volume, there's a lot of potential pavement damage, and that's another reason why we may want to lean more onto the concrete pavement. Signalized intersections, though, at least in District 6, we typically will put, 200, 300 feet of concrete pavement approaching the limit line, because that's where the trucks are slowing down and accelerating. So that's why looking at the pavement, not just at roundabouts, but other types of intersections is important. So there is one question in the chat, and a couple questions. The first one is, there's a different pavement I've been noticing on exit off ramps or freeway junction ramps. It makes a similar sound as rumble strips. What is that called? Any idea on that? I'm not aware of any special kind of pavement we're using on off ramps.
Not really sure what that would refer to. Maybe this is the grooving of the pavement itself, because the concrete pavement is textured, but we usually stick to our JPCB or CRCB, and on an off-ramp and on-ramp situation, it would be JPCB most likely.
Yeah. Yeah, so I'm a little bit at a loss at that question as well. Yeah, if there's more additional details or the location you could provide, we could probably answer that a little more accurately. The second question is, if short JPCP is only for low volume traffic, how do they have that certain portion in Texas where it looks like there is heavy vehicles passing?
Right. As I mentioned, as long as the average annual daily truck traffic is below 2,000, this is permissible. So you can expect that within like an urban environment within the city, on ramps and off ramps. If you have a lower volume of traffic, this option might be suitable. But mainly within the city itself, like this, you will not see this on a highway situation or a freeway. This is limited like to some type of urban environments.
Okay, very good. And I do see in the Q&A box about the location I-605 and SR-91. So we'll try to talk to our friends in Southern California to find out more about that pavement. So yeah, I think we're at time. I just want to thank you, Mohammed, for sharing your knowledge. That was very useful information. So appreciate it. Thank you so much.
Thank you.
Okay, so I am up next. I will be giving a 10-minute case study on District 9. This is in Bishop. So District 9 asked District 6 to help them do an ISOAP for an intersection that has an elevated crash history. And I had some members of my staff, and this is what they've put together. So I'll provide you with some background and the recommendations. So before I kind of show you the aerial, I'm going to go through all the stages and steps and just kind of walk you through how we actually go about doing ISOAP. So step 1.1 is just determining whether ISOAP is required. At this location, it's an existing two-way stop. They're looking at potentially installing a traffic signal or a roundabout. So yesterday we talked about what are the applicability requirements. So if you are changing the type of traffic control, that is one of the applicable criteria. So we need to go through ISOAP. So the intended project outcome and gathering data. So this is what we're trying to document. Why are we doing this project? And for this location, we have an intersection that has was triggered by one of our monitoring programs. So the district did an investigation. And so we have a safety concern that we're trying to address. So we want to go and gather what available data that we have. So some of the data is obviously we have the location. We have some of the key issues. We need improved pedestrian bicycle facilities, and I'll show you a photo. And then the proposed solution is a roundabout. So gathering some of the data, this is an aerial of the intersection where north-south is US 6, Y road is the county road that goes east and west. And towards the bottom corner, left corner, you could kind of see a portion of US 395. And that's where the highway makes this sweeping curve. And US 6 kind of peels off in a northerly direction. So this is a location that doesn't have full, complete streets. It has some partial sidewalks, partial bicycle infrastructure. Truck traffic is about 10%. One thing I'll note is there is an airport to the east, and there's also a mobile home park. So this is an area that will have a lot of trucks with freight and oversized vehicles. And there are a lot of driveways. This is more industrial, commercial type land use here. So still gathering more data. We get the lane configurations. We get existing traffic volumes. And we show that the volumes are actually fairly low. The state highway, only about 4,000 vehicles. The county road, slightly more than 2,000. And then for projections, we have a fairly high growth rate, 2.73. But when you're starting out with the low volumes, you'll still have future volumes are low. So this will definitely be in the realm of a single lane roundabout. Speed limits, 35 miles per hour. So I mentioned earlier about the land use and the trucks. So this is a location we definitely need to design for STA trucks, but also accommodating those oversized loads that are coming to and from the airport, as well as the mobile home park. So we want to look at what specific movements do we need to accommodate this particular location. We do want to accommodate all turning movements for the large loads. So looking at street view, we could see this is looking south, I believe, and we have left turn channelization on the state highway, and the county road on the east and west, they come to a stop. You could look at some of the partial pedestrian infrastructure. You see the power poles. Notice that very close to the corner. So this is a view looking south. So at step 1.4, this is where we're starting to look at various footprints and potential intersection forms. So we want to see what we could fit in without encroaching too much and just elevating the costs. And so we want to look at a right-of-way map, and you can see that the right-of-way is actually fairly tight on the county road, only about 60 feet. The state highway, the south leg, is 80 feet. There's one little corner cutoff, but this is a fairly tight right-of-way at this location. So you could start thinking, if we're going to be putting a standard size roundabout, and for a rural location, have a lot of trucks, oversized loads, 150 feet is a very comfortable size. Potentially could be smaller when you are in a constrained location.
I know, me too. Me too.
Okay, step 1.5, looking at transit, as well as taking a little bit deeper dive into freight and trucks. So as being a more rural location, there isn't any kind of fixed route transit with a stop right there. There's kind of a rural transit line that kind of passes through. It's also noted that the bus fleet is transitioned to hydrogen. But again, this is not a location that we need to have a robust transit infrastructure at this location. And we've talked about earlier about the truck needs, accommodating the oversized vehicles and STA trucks. Our initial safety assessment, this is where we're looking at what available crash data do we have. So at Caltrans, we use our TASIS database. We were able to pull up 3-5-year collision data as necessary. So this location was already triggered by our TASIS Table B report. And if we look at the 3-year history, we have 9 collisions. There's no fatal crashes, but there is a fatal and injury collision rate approximately 3 times the statewide average for typical facilities. So it is an elevated crash rate at this location. So next step is eliminating infeasible strategies, 1.7. So the 2 strategies that we do want to eliminate is one is the no bill, right? That is not going to meet our intended project outcomes or the needed purpose. We need to have a safety issue that we need to address. The 4-way stop also eliminated. In this case, this is as unbalanced flows. But as Jerry mentioned before, that always stop isn't necessarily a safety countermeasure. It can be. This is something that really has to be looked at case by case. Is it appropriate to put an always stop at a location? Generally, as the intersection gets more and more lanes, turn lanes, more through lanes, it just becomes more and more chaotic. There's more potential for conflict. So generally, it's not ideal to have an always stop as your ultimate traffic control. It can be an interim traffic control for another improvement, though. So our focus at this location is really going to be on that signalized intersection or the single lane roundabout. So because we have 2 viable alternatives, we need to go to stage 2 of ISOAP to figure out what is the best performing alternative. So the first thing we do with step 2.1 is go through the highway safety manual. And this is where my staff, did the whole learning curve, looking at the, similar to what Bernice went over earlier about finding the appropriate, crash modification factors. So we look at the baseline condition, which is the no build, and we get the number of crashes, compare it to the roundabout alternative and the signalized intersection. So we do show that our potential build alternatives will have a improved safety over the no build. The roundabout is about half. The signalized intersection is about 1/4 as far as the crash reduction. We also need to do the detailed operational analysis. So this is where we would typically look at DPHD, as Lillian explained earlier, but sometimes looking at the level of service just provides some good information. So at this location, because it's relatively low volume, a single lane approaches works, whether you're working with a roundabout or you're working with a signalized intersection. So we don't really have any capacity issues whether we go with a signalized intersection or we go with a roundabout, but you can see that the roundabout works best operationally as far as having the least amount of delay. But even the no build gives acceptable levels of service. So from an operational point of view, all these work, but you will have various delays that will go into the cost benefits calculation. Okay, determine the functional sketches. And here it's important to develop a layout enough that you could get a pretty good cost estimate, because that's really going to be key as to what is affordable. What is your available funding? For a safety project at Caltrans, what we look is at the safety index. Can we meet the thresholds where we could justify having a safety project from the shop? As I mentioned earlier, the designer laid out a 150-foot roundabout. And as I mentioned before, this fairly tight right-of-way. What we try to do at this stage is try to avoid building structures, things that are expensive. I showed you earlier, there's a power pole, there's going to be utilities that are going to have to get relocated. And you want to do performance checks, as Gina talked about yesterday, because if you start having to make tweaks and it's really going to affect your right-of-way, that could very significantly affect what the cost of your proposal is going to be. So looking at the signalized intersection, we also need to see what the impacts are. But because the footprint is much tighter than a roundabout, there's going to be less impacts. This is just a concept. Things may not necessarily line up perfectly on this concept, but we kind of have an idea that a lot of the crosswalk or a lot of the sidewalks were already laid out for a future signalized intersection. So less impact than a roundabout, which is no surprise. Okay, step 2.4, doing a cost estimate, life cycle cost. So we want to develop a cost estimate, and generally at Caltrans, we're only looking at construction cost and right-of-way cost when we're doing our benefit cost ratio. So my staff used this guide from FHWA, Highway Safety Benefit Cost Analysis Guide. This is just one tool that can be used, but definitely this is not something that has to be used. So this particular document just kind of spells out what some of the potential costs that can be used. And some of the things that we would typically use in our benefit cost analysis would be, besides the construction and right-of-way costs, it would be maintenance costs, operational costs, energy costs. You also have the crash costs, you have the delay costs, but you could also add things, potentially, air pollution costs. These are a little bit less tangible. but also looking at life cycle costs. Eventually the signal equipment is going to have to be updated, replaced. Things are going to have to be refreshed. So all those things can go into the cost benefit analysis. So this program did some calculations which showed that the roundabout alternative gives about $18 million worth of benefits over the life of the project, compared to $12 million of benefits for the traffic signal. So step 2.5 is putting all the costs within a matrix. And what you could see is for the roundabout alternate 1 and the signal alternate 2, it gives almost an equal cost benefit for the estimated cost of $4.5 million for the roundabout and about $3 million for the traffic signal. So if you look at this matrix, you'd almost think all things being equal, but we do know that in the end, the roundabout would have more safety benefits as far as reducing the number of serious injury and fatal crashes. So if money was no object, this would kind of lean towards going to the roundabout. So as it turns out, this was kind of like the first cut. This is just the draft, but as the project engineer fine-tuned the cost estimate, the cost of the roundabout actually escalated multiple times to the point of being $17 million for that 150-foot inscribed circle diameter. So if the cost went up by 4, then the benefit cost ratio would go down by a factor of 4, or 1/4. So essentially, assuming that the signal remains at $3 million, we're at a benefit cost ratio of 1, and the signalized intersection has a benefit cost ratio of 4. So that actually shows us now that the signal is giving us more bang for the buck. So what do we do at this point? Well, we still need to kind of refine our design. And could we actually get the cost of the roundabout down? Because we do feel that it would still have better safety outcomes. So that's one thing that they are looking at, is potentially reducing that cost by going to a smaller and even into a mini roundabout. Okay, so this is still a draft, but that is the intention. We are looking at potentially doing a lower cost, a compact, or possibly a mini roundabout as this project continues to be refined. Okay, so the next session I really quickly want to cover was locally sponsored projects and local development review, because we see a lot of projects that local agencies want to build on the state highway system. They have to go through our processes for approval. So local agencies or developers, they normally work with our planning division. And if they propose a new intersection or a improved intersection that triggers ISOAP, eventually ISOAP is going to have to be done by somebody. Typically, it's going to be the local agency or the developer hiring a consultant. So the best thing is come to Caltrans and do early consultation. So ask us, is this something that will potentially be approvable? Just share what the concept is, and we'll just get some initial feedback, because we don't want someone to spend a lot of time and effort for something that just is not going to be approved. So if the proposal is viable, ISOAP could be done during the planning process, during the local development review. And a lot of the projects are going to go through the QMAP, Quality Management Assessment Project. So it's not going to require a full-blown project report, but there are a lot of applicability criteria whether a project can go through the QMAP process. But a lot of times local improvements do go through that process, but if it's more involved, where it requires things like right-of-way dedication, and there's a whole checklist, then it may have to go through a project. I'm sorry, QMAP still could do right-of-way dedication, but if it's something that's even more involved, very high cost, then it would potentially have to have a project report, have a PID document written. but you want to talk with our planning division to see what is the path forward. So as far as the roles and responsibilities for ISOAP, ISOAP can be prepared by either the local agency, a consultant, or by Caltrans staff. Generally, for Caltrans projects, we are going to be preparing the documentation. But if it's locally sponsored or privately sponsored, then ISOAP will be done, typically by a consultant or potentially by the city. And the Caltrans is going to be more reviewing what's being submitted. So the ISOAP engineer prepares the ISOAP. Typically, it's going to be a traffic engineer that does the ISOAP, but it could be just a design engineer as well. But we'll need to have a traffic operations assessment as well as a safety assessment. And the project engineer would be developing enough detailed geometrics to get a good cost estimate. So for Caltrans staff, every district has at least one district ISOAP coordinator. This is the person who's going to process all the documents. And it's going to get concurrence from the traffic safety engineer if everything looks good from a traffic operational standpoint. So the district ISOAP coordinator is going to be working with various functional units, traffic operations, and traffic safety. So one thing I want to talk a little bit more about is when the right solution is not necessarily affordable right now. And I talked about this yesterday. We don't necessarily want to just build what's cheap and easy and be stuck with it. If we could find a path forward to what we want to have built, we want to look at how do we go about finding more money? Can we do some kind of interim improvement? Can we do something that's built in phases? So this is where we really want everyone to get your thinking caps together and have a collaborative meeting internally, externally to find out what the right solution is and where additional funding might be. Maybe it's applying for grants somewhere. Maybe it's developer fees. Maybe it's just having a plan and then developing some kind of mitigation fee program. So I want to talk about a couple projects in District 6 where this is exactly what we did. We didn't necessarily want to go with the traffic signal, but we wanted to figure out what could actually be done. So one location is in the city of Lemoore. This is the Bush Street interchange. It's not a very old interchange. It's about 15 years old. We already are experiencing some operational issues with a ramp backing up. The city went ahead, had a project study report to look at building a diverging diamond interchange or a full-blown multi-lane roundabouts. Those improvements cannot be afforded in the short term. There's development pressures to build more housing. What can we do in the short term? So this is where we started looking at, can we build temporary roundabouts or some kind of interim configuration? So that's exactly what path forward. So there are going to be 3 roundabouts. One is at adjacent local street, and then at the ramp terminals at this tight diamond interchange. This is going to be kind of the quick build or quicker build in the case of Modesto, where it's going to be a lot of paint and plastic, but we are actually going to be pouring some concrete for the splitter islands and some of the central islands. But this is not a permanent 20-year solution. We do hope to get maybe a good 10, 15 years of design life. The more improvements that we build now is less money for the future reconstruction. So we don't want to overbuild right now. But as developers are building more housing, more money will be collected for the ultimate improvement. The other example I want to give is Highway 137 in Tulare County, just on the east side of the city of Tulare. And we had a home builder who had a requirement to build a traffic signal before their next phase of houses. And this is a location that was going to be ultimate 4-lane conventional highway. It was already set to have a signalized intersection. So that's where all the curbing was placed. Because of supply chain issues, it was going to be a challenge to get a signal in a timely way. manner. And what I initially proposed was, well, let's look at putting a temporary roundabout until we really need to get that permanent signal. And as the costs escalated for the temporary roundabout, as we were, being concerned about pedestrian crossings and, various features were being added, we started to think of, what if we just did a more permanent roundabout? It may not be the ultimate configuration, but it will be giving us better safety outcomes than a traffic signal. And then maybe eventually we could build an ultimate multi-lane roundabout when the north lanes get developed. So we worked with the city, where the developer, they contributed $350,000. So even though they had to build the signal, under this scenario, they would just contribute $350,000 towards the roundabout. We were able to come up with, from our minor program, $1.25 million. And that's something that will not always be readily available. And we also have to look at, are these improvements going to have independent utility when we start mixing and matching funding? So this is a before look at our intended 4-lane conventional highway. This was the plans that the home builders developer came up with fitting in a compact roundabout. Originally, I was looking at a mini roundabout, but we were able to go with a compact roundabout, slightly less than 100 feet. We're accommodating STA trucks on the east and west of State Highway, but not necessarily turning into the residential areas. And this was some photos from construction a couple months ago. So this is just kind of wrapping up construction right now. Okay, so the last segment, I'm going to be talking about public outreach. So public outreach is becoming more and more important at Caltrans. We really want to have projects that really meet the needs of the users and the communities where our highways pass through. It's not, our way or the highway or whatever the saying is. We really want to work with the community and meet the community with where they're at, making sure that we're accommodating their needs, their modes that they are using, looking at the context of the highway. So we have more and more public outreach being built into our processes. But sometimes if you're looking at different types of configurations, we may need to go beyond what our standard processes are, particularly if we're looking at more innovative type solutions that may not be readily understood by the public. Late in the process, we may have new variations or new alternatives where we want to go out and just get more feedback and make sure that the public really understands what we're proposing, how it's going to operate. And not only for the public, but also local officials. So it's important to identify what are some of the potential concerns that the public may have. It could be things dealing with safety or congestion, access to adjacent properties, particularly if we're going to be taking away access, if we're going to be consolidating access, if we're adding, raised islands where now we're restricting certain left turn movements. The public may have concerns about speeding. They may want things like traffic calming. Parking is always a concern where you have on-street parking that may be taken away. Or if we're going to be acquiring property that may take away parking potentially from adjacent properties. Bike and pedestrian access and facilities. Truck access, how are truck deliveries going to be delivered? How are agricultural vehicles going to go through the intersections, or whatever type of vehicle needs to go through the intersections? And are there some potential controversial intersection configurations? There you're going to have to spend a little bit of extra time and effort. Quickly going through some examples here in District 6. So this is Highway 190 in Tulare County again, between the city of Porterville and going up into the mountains to retirement community towards the east. There's a Native American reservation to the south, and that's a park and ride lot. And we have a quarry to the north, so we're going to expect to have large trucks and a lot of loads going to the quarry, potentially oversized vehicles, and we have a gas station right at the corner. And there's always concerns about access to gas stations. So we proposed a roundabout at this location, and this is a location that had a high collision rate. And the collision pattern where folks were pulling out from the side road and broadsides. So we had a couple alternatives, a roundabout with a good size 150 feet or so roundabout, and then we had a signalized intersection alternative. The signalized intersection was actually more expensive in this case than a roundabout because we had to do some profile correction on the state highway. We did have a public meeting. The roundabout wasn't necessarily well received by everybody. There were some people who did like it, but the property owners had a lot of concern, particularly with the corner, the quarry on the north side. Someone did put a billboard saying 190 roundabout here, really tell Caltrans no. And they also posted the project manager with his phone number. The local newspaper had an editorial that said Highway 190 roundabout lacked input. This editorial says that we and many others have concern. First motorists will be traveling along 55 to 65 miles per hour and have to slow to 50 miles per hour to negotiate the roundabout. Very dangerous. So this is their perception that a roundabout would be dangerous at this location because people have to slow down to go through a roundabout. So at the public meeting, we did try to alleviate or allay their concerns. We kind of explained why we're doing, but the newspaper had this editorial. They also had a Facebook page, and there was a lot of social media chatter about this roundabout. But we really tried to proceed with the roundabout, which really was the better solution. We worked very closely with the Native American tribe because it did affect their park and ride lot. But we did work with them as far as introducing some elements of their culture as far as with our landscape architecture treatments here. So this is one of our more attractive roundabouts. And after it was built, very well received, and essentially there were no complaints. With the quarry, we had a lot of interaction with the quarry. And we developed a second roundabout or second truck apron to accommodate the very large 200-foot loads with the lowboy that he has about twice a year. So this was a success story. And once we get one roundabout that works well, it really helps when we could point other communities to this works here, this could potentially work well in your community. So the other roundabout I wanted to discuss was in the community of Prather. This is up on Highway 168, Fresno County, up towards Shaver Lake. This is Auberry Road, which is a county road, which carries just as much traffic as the state highway as it's coming up the mountain. This is a 5-legged roundabout and a lot of interaction with the community because this was very controversial. We had multiple meetings at the school. We also met at the pizza parlor with some of the business owners and residents. We walked with the gas station owner. We tried to explain what we're doing. And we tried to address their concerns. One thing you'll notice here, we have very, very short splitter islands because having that access, easy in out, left turn access for their RVs and things was really important to them. Even though we felt that having longer splitter islands would accommodate all movements, we still worked with them. And we did a little bit of compromising, but in the end, it works. We don't have any really negative safety issues with these shorter splitter islands. And this is another roundabout, a lot of controversy. It was built, works extremely well, and people really appreciate it. It's so much easier now to pull off from Auberry Road, whereas they used to wait a long time to try to get on the highway. One thing that really helped us at the public meeting was having the CHP there, because they were able to explain what the crashes that were happening. When we explained these were the types of crashes that were happening, the response was, we never see any crashes. So they were able to provide backup and support, which was really good to have. The other thing I want to mention is this, the very, very large creek fire that happened a few years ago up on the mountain where half the mountain burned down. This is the area where we had the turnaround. And you can imagine it'd be very hard to turn around at a standard rural intersection. So this is one very easy way to provide trucks to turn around. And if there's a PSPS power shutoff, this roundabout's going to work, whereas the signal may potentially go dark. Okay, lastly, very recently, we had a public meeting in the small community of Stratford, which is in Kings County, about a half an hour south of Fresno. This is a community that feels they've been left behind. We recently got a lot of complaints about, wanting left turn channelization when a gas station was placed in one of the corners. But when we went through local development review and we did the analysis of left turn channelization, it didn't meet warrants. We did not require the developer to put left turn channelization. But the community felt very strongly that they need to have left turn lanes to go into the community. They contacted us, and we want to have a public meeting, kind of a listening session, to understand more clearly what their concerns are. So we looked at a couple options, potential left turn channelization. We don't really have crash history that justifies a safety project, and certainly not the crash history to justify a roundabout. But we want to see is, can we actually build a low-cost roundabout for maybe about $2 million? And one thing I didn't mention for that previous roundabout in Tulare, that roundabout was a total cost of about $2 million. About 1.6 million. I mentioned before, $1.25 million that we contributed, and 350, so it was about 1.6. At this location is more of a rural location. We may have to add some pedestrian facilities, but we want to see is, can we work with about 2 million where we could provide some money, perhaps the local agency or some grants to develop a project. So a lot of people showed up to the meeting, 170 people. It got very, very heated at times. What we did not want them to feel is that this was just going to be lip service, that we're just going to listen to them and nothing was going to happen. And that was one thing a lot of the people in the community feel. They mentioned that they had a meeting 10 years ago. They brought up the concerns and nothing happened. However, that meeting was not a meeting with Caltrans. It was either a meeting with the county or it was a meeting with some other group, but it was certainly not a meeting with Caltrans. But this is where they felt that they were not being heard. So we really tried to listen to them, and we're looking, very carefully about what our next steps are, because we don't want to lead them on and promise them anything when we know that it's a lot of times it's difficult to get projects to get funding when it's not going to be something that meets the safety warrants where Caltrans is going to automatically be funding a safety project. So some of the tips I just wanted to leave with is the environmental division, when you go through the environmental process for the various documents, they have a lot of guidelines as to how to have public meetings. But a lot of these meetings aren't necessarily to support a specific phase of a project. It's more about outreach, listening to the community. So it has a lot of good information, but we don't necessarily have to meet all the specific guidelines. So just kind of do what makes sense. But every Caltrans district now has a community engagement coordinator. And for this meeting in Stratford, we worked with our coordinator. We had meetings with community representatives, every 2 weeks. We really wanted to have a meeting that really was going to serve their needs. So for instance, we had Spanish translation at the meeting. It's good to have a workshop format separate from the city council or board of supervisors meeting, because when you're piggybacking with another public meeting, you lose control. And we want to have full control of the meeting, of all the logistics. And it's best to have our meeting in a place where the attendees are going to be comfortable, which may be a community center or a school that they're familiar with, right in the community. I'd like to give a presentation that will address a lot of the concerns from doing research beforehand. We want to find out what their concerns are going to be. I like to just hit those head on in a presentation. And it's good to show videos that could maybe counter some of the perceptions. So I've shown videos of very large vehicles go through roundabouts when I know that's going to be an issue to a community. And a lot of times that really kind of alleviates some of those concerns. Questions and answer. It's important to have people to be heard. There's different formats. There is some risk to give a microphone to somebody and they could roll up the crowd. However, that's something I actually like doing because I know that people like to listen to what questions or comments other people have. In the case of Stratford, there was definitely some rolling up of the crowd, but in the end, I thought, it's okay. They threw some figurative, tomatoes and things at us, but we try to respond, to them and not let our emotions get bent out of shape, even though it was very heated. People got very emotional from the public. But it could be you provide comment cards, you could screen questions. So there's different formats. If you are expecting a lot of controversy, you could have a different format where people just kind of more of an open house with tables and easels and things like that. So it's really going to be a case-by-case basis. Very important to listen to with empathy. And because people may be very emotional, they may have people who have had loved ones who passed away. So it's very important to listen with intent and be compassionate. Having law enforcement is good. As I mentioned before, the CHP, they were able to talk about the CHP statistics. Second reason to have law enforcement is if the crowd gets unruly. If you're going to have the first roundabout in a community, having a roundabout rodeo can be very, very useful and informative. So we did that in the city of Kerman. So if you do a Google search for Kerman roundabout, you're going to show a 150-foot roundabout we built in an open field. We invited people to bring your trailer, bring your RV, bring your fire truck. And it showed that the equipment can go through our planned roundabout. And if there are public officials who may be skeptical, have a lot of concerns, it's good to meet with them individually rather than in public, because public officials often behave differently when they're with their constituents. So it's good to meet with them, one-on-one or with the city or county staff. Okay, so at this time, do we have any questions, Jerry?
Yeah, we do, John.
Okay.
And they were actually the question that I see first and foremost. A couple came in, and they were with respect to the case study, the example in Bishop. I think that was one of the first ones you covered.
Okay.
So I probably should have interrupted you, but let me see. This is a question about which software tools were used to analyze delay and level of service at the roundabout and signalize intersection alternatives to ensure a fair comparison.
Okay, when it comes to analysis tools, and this is something where calibration makes all the difference in the world. So for roundabouts, we will typically use Sidra. For signalized intersections, we will typically use Synchro. But there's different settings that can be used. And at Caltrans, we have our standard types of adjustment factors. So we definitely want to have a level playing field and not skew the results.
Okay. The similar question, step 1.6, where did you get the fatal plus injury collision rate? Again, same project. And does a different level of injury have a different weight?
Okay, so yeah, this is something that is in transition right now. And Jerry, you could actually talk about our new TS&R replacement project. Yeah. So in the past, we did not really distinguish the levels of injury, where it was just the injury could be from of pain all the way to serious injury. With our new system that will be rolled out this year, we're going to have 4 layers or 4 levels of injury. And our new programs, which Jerry, I know you'll be able to address for the safety index, is going to adjust for the different levels of injury. So as far as the collision rate, we took it from our current process, but going forward, and what we're talking about in a few months, that's when the new the platform will be deployed. So we will be transitioning to the new system. And Jerry, I know I think you want to mention more on that. On the new safety index?
Yeah, John, sorry, I got distracted. I just wanted to maybe mention and help me if I'm heading off in the wrong direction. But we are adopting very shortly a new approach to calculating the safety index after 3, 4, 5, probably decades at least of this legacy system we've been using. And the new system or approach is really more like a spreadsheet tool than anything, very similar to this collision cost analysis spreadsheet tool with a lot less input. Once you have the data that needs to be entered, it's a matter of moments to calculate the crash cost savings and the benefit cost ratio. Is that what you were looking for, or?
Yeah, exactly. And we were expecting this to be out already, but you know, any new IT projects, it takes time for all the bugs to get worked out. So it's been delayed, but we are hoping in the next few months that will be released.
Yes, it's probably more a matter of timing with other changes that are happening at about the same time.
Yeah. Okay. If there's no other questions, Jerry, would you like to go through the exercise now?
I would like to try. Yes, I would. John, you have control of the screen for me?
Okay.
Okay. Well, John, stop me whenever you want to. I've got 3 or 4 lined up, and I want to start with a quick case study. Didn't get a chance to do this yesterday, but made a reference to this. So I'm going to jump back into the first case study or exercise here is really about an affordable roundabout design, a safety problem that warranted a quick response. And in this case, this goes back a decade or more in Virginia, where they basically implemented one of the first instant roundabouts at a large intersection of a two-way stop controlled intersection, where they had a clear pattern and concentration of crashes, injury crashes in particular, because speeds, at least on the free-flowing roadway, were, I think, about a 40 mile an hour. So what you see pictured here is a picture of the temporary instant plastic roundabout that was installed, I believe, in 6 days after about a 5-month process of designing and getting local support for this. You could see the results of this 3 years later, 2-3 years later, they did an analysis and found that about 90% of the broadside crashes had been reduced. So the before-after assessment. Equally important, maybe in some other cases, was the fact that they had about a 3-4 minute wait every morning at this intersection for the stop control traffic. That delay congestion was immediately resolved the day that the temporary instant roundabout was open. So it showed the operational capacity advantage, mobility advantage, as well as a safety advantage. Jump to the next slide. So again, the other thing, the result was ultimately community liked what happened, obviously, and a permanent roundabout was installed in 2019. Next slide. Go one more. Okay. As I said, they had a 30% reduction in all crashes, 90% the queue, and this merited and won a National Roadway Safety Award. And you see a little bit better what they did here on the scope on this aerial photograph. You might say they did a little bit of overkill, a long approach roadway treatments in order to slow people down before they got to the roundabout, even for those that had previously been stop controlled. on 3 of the approaches here, but you see a really nice design, a lot of deflection. The ultimate permanent roundabout, a lot shorter on the splitter islands, actually. I do want to mention also that, well, let's go to the next slide, because I think what's really important here was the processes you just went through, public engagement. As usual, this was not easy for the community to accept. They had a problem. I think in this case, Virginia DOT proposed a roundabout, and there was not a lot of positive support for a roundabout at this neighborhood location, residential neighborhood location, rather rural. And what VDOT did was proposed an instant, a pilot project, which you just saw picked versions, photos of. And again, what happened was that based on the immediate relief from the operational problem and then seeing the crashes go away, the residents asked for a permanent roundabout. The last part of this that's important to notice, mention, is that this led to a question, because during the 3 or 4 years that plastic roundabout was in place, and this is snow country, by the way, they had a lot of maintenance headaches. A lot of pieces had become dislodged or broken, had to be repaired or replaced. So this led to the questions about a more durable plastic system, and that led ultimately to this contract, where we now have systems that are being that Phil Rust in the city of San Diego are now using for permanent installations. Quick build, low cost, and relatively easy to maintain. Not as easy as a traditional method, but that remains to be seen. We don't know, but the expected life on these durable materials now is probably at least 50 years. The connection is what we need to be watching out for. And that's why these will be piloted within California as well before some formal adoption of using this material. Okay, I'm going to go to the next one. This is, again, a very important case study I wanted to share. And I mentioned this yesterday. This is a project the city of Cleveland presented to us back at the end of 2024, a mini roundabout corridor. And what you see here is a map that showed this corridor about 1.8 miles. Several traffic signals and a stop control at one end of the corridor, and actually a roundabout at the other end of the corridor. And in this case, the purpose and need of this project was safety needs. There was speeding, a 35-mile-an-hour corridor out here. All residential, older residential neighborhood. And again, you could imagine speed with coordinated signals or red light running. There were severe crashes. Pedestrians in particular had been killed. So after, probably a decade of trying to figure out what to do, because this corridor already had been equipped with traffic control devices, or over-equipped, the proposal came up to do a corridor converting 7 of those existing traffic signals. Next slide. So this is the post-project conditions. 7 roundabouts replace 7 traffic signals. And the cost, let's go to the next slide. So the cost of this project total, and this was completed, I think now 2 years ago, or a year and a half ago, was $3.5 million, 7 mini roundabouts. And as we look at photos, you'll see that the work that was implemented was relatively minor at each location because the infrastructure and speeds and traffic basically permitted that. Let's go to the next slide. Okay. And the post-project results, of course, and they did an immediate evaluation, or periodically after all of these roundabouts had been opened. There was 2 phases to it. But what they focused on initially and what they wanted to do as an objective was reduce speeds in the corridor, because over that 1.5, 2 miles, there had been speeding and crashes, and all, again, residential area. So what they measured almost immediately was a significant drop in the 85th percentile speed down to 27. So dropping from about 36, 35 miles an hour to 27. And so since this had been signed at 35 mile an hour, a speed limit, they immediately went and implemented a 25 mile an hour speed zone in this location or along this corridor. And then they actually had recorded or monitored, and they had found only 1 recorded roundabout involved crash in the after period, and that was after just about a year. So, more time is needed to fully evaluate the safety benefits. Okay, next. So again, just want to give everybody a chance to see the kind of a minimalist approach, if you will, but these all are raised, mountable, fully mountable central island and approach islands. And again, they have the photos of the design vehicles going through here without much pain. Next photo. And again, just to give you an idea again on a scale, the existing intersections, no work on the curb returns, but I think they did cut in this case, you would see lower right that they actually built the, for that cost, they included the curb ramps. Okay, next. And again, just to emphasize the speed reduction, new speed limit and crash reduction. Okay, let's move on to the next one. Oh, sorry about that. Next one. Okay, this is something I showed yesterday. I wanted to spend just a little bit more time on it. I think it deserved that because we, as I might have mentioned yesterday, we really haven't been taking advantage of some of these safe system or alternative intersection concepts. And one of them on the state highway system is the R-cut. Okay, and when I say this again, I'm talking about a reconfiguration that allows U-turning by the design vehicles. And so while there are a lot of right in, right out driveways, those have more impact on commercial vehicles. They have to find alternative routes circulating around so that they can make a right and a right and a right to make a left instead of a simple right U-turn and then come back to the intersection. So this is an example of where, and they're rare and hard to spot, but this is a kind of a good demonstration of the concept that was implemented in the Bay Area. As you can see, an interchange with Powell Street is the local street there. And you can't really see a lot. You see the northern ramps heading northbound, and on the left side, a hook ramp configuration. So a lot of the traffic generated here from the right side of the screen or east would come through this undercrossing and then turn right to access the hook ramp in order to go south. Okay, now this is a very busy area, a lot of congestion. During peak periods, this would be overwhelmed. So the relief that was proposed and implemented here was to allow drivers and really passenger cars only, because what they provided, if you look heading east to west in yellow this time, you'll see that passenger cars are able to go past, it's about 800 feet or 700 feet, I think, past the interchange and make a U-turn. Does not accommodate truck traffic. And that's not necessary because trucks are accommodated by the hook ramp, right? So this is a very important second opportunity or option for commuters during peak period because it reduces the demand and congestion on the hook ramp intersection. And then drivers just go through along Powell Street, they make a U-turn, come back, and they have basically a free right almost to get on the southbound diagonal entrance ramp. Next slide. And again, just a little bit closer look, you can see the yellow is what all traffic does off-peak, let's say, and also always trucks are using, design vehicles are using the upper with the yellow configuration. And then on the bottom, you see what is available anytime, but usually during peak periods. Again, commuters, for instance, can use the U-turn there. What's important to note is that the travel distance is about the same. So there is no out of direction in this case. And the travel time is usually less for the diagonal entrance ramp. So really a simple, easy way to relieve congestion at an interchange. Okay, I don't know if you want to go one more, John. This is the last one, actually. Could be. And this is really would have been meant to be more of an exercise when we've had workshops in person. So this is another case study, and this is a good example of how to use the ISOAP process to use it as a tool, as opposed to comply with a number of process steps. This is a rural 2-lane state highway where, as the yellow diamond indicates, that's where a new public road intersection was proposed. And this goes back to 2013, maybe a month after the ICE policy was adopted. And in this District 4 proposal, this led us to meetings to talk about how we needed to plan all the ICE studies in order to make a decision about this new public road connection serving planned development. Okay, you can see there a big ag area, and you see some development or activity on this shot. Let's go to the next screen. Okay, so that gives you an idea of the scale of what was proposed. And so this is now moving forward. But just think of this as a development plan that was presented and a developer seeking a permission from the county to build this and Caltrans to access the state highway, high-speed rural state highway for this planned community here. Okay, so the ICE at that point, or ISOAP process, was to look at alternatives here. And you can imagine that a traffic signal was probably one of the first things that was looked at, and in terms of are warrants met for a traffic signal at this location. In this case, as you might see from looking at the screen, there's three roundabouts already shown within the development. They were interested in a roundabout, building a roundabout, and really nothing else at that time. Of course, they would do whatever Caltrans required of them. But in this case, they proposed a roundabout. And of course, the discussions that ensued were about, okay, how are we going to evaluate this project? Okay. Well, most importantly, we talked with our operations group. We talked with our safety group. We talked to the city, the public agency here, City of Gilroy, I believe. And everyone was okay with the estimated performance that a roundabout would provide here. You had the usual concerns, high-speed environment, how are fire engines going to get to the development, all the usual questions about roundabouts. And because the city totally was on board, they embraced the roundabout as well. And again, we knew the safety benefits, and we knew delay would be less than with the traffic signal, not to mention less operational and maintenance costs that were associated with traffic signals, the expense there. Basically, we seem to have an agreement moving forward to go ahead with the roundabout. Now, what did that mean for the studies, and what did that mean for documentation? Okay. Well, this was a kind of a perfect opportunity to demonstrate how easy this new ICE process and policy could be. But there was one glitch. Next slide. So this showed not a lesson learned, but actually the developer at that point didn't even really talk about or show us plans for what was proposed on the north side. So the good news here is, and this is relevant most of the time, they own both sides of the road. And so sometimes when you propose, a developer proposes improvement in a narrow right-of-way, they're reluctant to do something that requires buying right-of-way that they don't own, right? That's a big problem for them, cost and or schedule-wise. In this case, it wasn't, and the roundabout turns out to be a almost perfectly balanced solution for all road users in this case. So what I want to end with is just by saying that the agreement was that the ICE process at that time, the documentation was that we completed stage 1, which was screening, and that there was agreement that only one alternative needed to be evaluated and pursued moving forward. And I think in a couple-page document, there was a formal agreement. We concluded the study process, and a permit was pursued. And you can see here now what was built at that location. So I think I'm just going to stop there and show that, again, as things have evolved and there's more understanding of what roundabouts can do, and there is now a lot more of these, at least in rural areas. There'll be maybe easier agreement, less work involved. If this is when these situations arise, when everybody realizes this is maybe a lower cost, more sustainable solution in the long time. So I'm stop there. Any questions?
Yeah, Jerry, there's no questions in the Q&A pod. But I'd just like to reiterate that point about going down to one alternative, because that could really kind of facilitate having projects move forward, where you do not have to analyze multiple alternatives in the environmental process, right? Now you could potentially just go with a CE and particularly when there aren't, when there's not a lot of public controversy. A lot of times the local agency also, they want the roundabout. They don't want to spend the time and resources to analyze the signalized intersections. So you could go ahead and reject that signal if it's going to be obviously poor performing. You just go with the better performing alternative. So keep that in mind, that you could actually save a lot of time and effort and go down to one alternative, and you don't have to go through stage 2 of ISOAP. This is where things are much more involved, going through the highway safety manual and such. So I think a lot of times you're going to stop at stage 1, and you could stop right there.
Yeah, I'll just mention, John, that I almost wish I had reinserted that slide from the safety analysis presentation, where that's probably what this would have turned out to be, is a traffic signal would have been less costly. But the crash over 20 years, the crash cost savings for the roundabout would have been higher than for the signal. And that would have been enough to say, hey, we know this is going to have fewer, even if it's one fewer fatal over a 20-year period. That is what can also tilt the scale.
Yeah. Okay, I'm not seeing any additional questions, but if anyone has a questions, feel free to raise your hand, go off mute, or just type something in the chat, or actually the Q&A pod. Otherwise, we are going to wrap up in the next few minutes. One thing I want to mention again is that every district does have at least one ISOAP coordinator, and these are the designated folks. This is on the Caltrans ISOAP website, so you have their email address, so you could directly contact them. So if you want additional training, you could contact them, and they could schedule training. Or if you have a specific project you want to discuss, feel free to reach out to them. And there is the Caltrans ISOAP website. This is an external facing website. And we do intend to add more and more content to this website as far as useful information, links, examples of ISOAP reports. And lastly, I want to mention that we do have an ISOAP TAP, or Technical Assistance Program. So if you do have a very difficult issue where you want to just get some minds together and do some brainstorming, answer some technical questions, feel free to reach out to members on the TAP who are also listed on the Caltrans website. So Lillian and myself are on the TAP. But I would say it's best to contact the district ISOAP coordinator initially. And if for some reason that doesn't work out, you could reach out to one of us.
John, if I may, I want to mention that informally, we actually have a couple partners from other agencies. For instance, Phil Russ from San Diego. He is a part-time technical assistance program team member, as well as FHWA intersection safety and design experts. So it's Caltrans, the folks with the most experience, and then knowledge and expertise. But we also are getting that perspective from local agencies and the federal government, the information that they possess as well.
Yeah. Okay. And a lot of questions about getting copies of the slides. When's the recording going to be available? And Scott, could you go ahead and answer that question for everybody?
Yeah, absolutely, John. We'll have links to the presentations and the recordings out before the end of the week. Everybody who's in attendance will receive a copy.
Yes, so we are going to have PDFs of the presentations available for everybody. The size of the PDFs are too large to email, so that's why there will be a downloadable link for them. Okay, we could get, I think we could conclude at this point. So Scott, if you have any other things you need to say before we close up.
John, thanks. It's been an amazing couple of days with you and your team. I appreciate your putting this training on for us and sharing all the knowledge you've got on roundabouts and intersectional safety. And I'd also like to thank everybody who joined us. We look forward to having you attend future trainings down the road. Did you want to have the presenters hang out for a couple minutes, John?
Yeah, we'll hang out afterwards. But the one last thing I do want to mention is that if people did not have or still want to submit questions, feel free to send directly to Jerry or myself, and we'll try to get back. And if there's other topics you'd like to see presentations on, for instance, we went through turbo roundabouts really quickly, and we think there may be more people interested in knowing more about turbo roundabouts, multi-lane roundabouts, more about affordable roundabouts. We're certainly open to developing, different training to help support ISOAP.
John, if I see we have a minute, can I,
Yeah.
I want to reiterate or emphasize the question that came in earlier today and the answers that were given so far. And this is about the historical issue that a lot of us used to face, which was some solutions are good for safety and some are not. They're better for mobility, and you're kind of sacrificing one or the other depending on what the strategy was. And I think always stop could create delay. Traffic signals has pros and cons as well. But again, an excellent question coming in is that how do we deal with that now in the decision-making process? And both Gina Lopez and I responded, and Gina gave a very good, balanced, objective response, is that it's case by case. Everything's important. Both are important, depends on the project type, but safety is a priority. I just mentioned again, the good news is that we now have 3 or 4 very good, affordable, or not expensive solution strategies that are good for both safety and mobility. So as far as intersections go moving forward, we may not be facing that challenge and issue because we can address both needs with one project or one strategy. So thank you.
Great point. Thank you.